from work. Just real quickly, a Tennyson warning. So this just means that we're recording this. So your likeness, your face or your voice might be part of this recording. So if you are uncomfortable with that, then you're able to leave, and then we could get you a video recording of this presentation if you're more comfortable with that. So just wanted to start with that. When you came in the door, you may have seen a table with a number of different resources on it. One is today's agenda that we're going to go through, as well as resources for understanding nitrate in southeastern Minnesota, because you'll learn today that there's a fair amount of nitrate that was found in groundwater in the county. And then lastly, there's a Houston County workshop survey. So when the workshop is over, if you're willing to fill this out, be much appreciated. Helps us do a better job next time we have one of these events. And then lastly, there are Part B atlases. And when I say Part B, that means the portion that the DNR worked on. And so this is the groundwater portion of the County Geologic Atlas. So feel free to take one of these. You can bring it home with you if you'd like. So with all that said, I will transition the slides now to my colleague from the Minnesota Geological Survey, and she'll kick off the presentation. And then if you are joining us from online, if you're willing to turn off your microphone, that would be appreciated. Okay, thanks, folks. Take it away, Julia.
Do I need to wear a mic or anything?
No, it should be picking it up from the table. And then lastly, there is a pointer. Yeah.
All right. Thanks, John. Happy to be here today and share a little bit about the geology of Houston County. The Minnesota Geological Survey did this work a while back in 2012, 2013. So this has been fun for me to go back to and think about all the work we did. I'll start here by just appreciating our funding. We get money to do our work from the LCCMR, Minnesota Environmental Fund, and we collaborate with the Department of Natural Resources. We collaborate in kind with work from Houston County. They helped do a lot of the water well locating back early on in the project, and we also get funds through for our atlas mapping through Clean Water Legacy Amendment. If you haven't heard of us before, the Minnesota Geological Survey is a small organization, about 30 people strong. We are at the Twin Cities campus at the U of M. We are part of the College of Science and Engineering, and it's our sole mission to serve the people of Minnesota through providing systematic geoscience information to support the stewardship of land, water, and mineral resources. So that's our website there. All of the products we produce are available as PDFs online if you're interested in learning more about the geology of Minnesota. And I'm going to speak about one particular mapping program in general called the County Geologic Atlas. And you can access all the County Geologic Atlases through that Map and Data Library button. If you were on our website, click on that. That'll take you to all of our maps, and then you'll get to a site like this. The U of M hosts all of our work through what's called this Digital Conservancy. So a lot of different subjects that our maps go into in reports, but the one we're going to talk about today is the County Atlas series. So if you were on our website looking for this information, that's where you'd go. You'd get to another one screen that would show you all of the ones we've done. So far, we've produced 70 of them for every county. Haven't quite made it to all of the counties yet. And that's where you could search Houston County and get to Houston County. And Houston County has 4 geologic maps associated with the Atlas package. The first one is the database map, which just kind of tells you where all the geologic data came from. And the second one is the bedrock geology map. So the units and their descriptions and what kind of underlying bedrock geology you have in the county. And then the third one is the superficial geology map. And the superficial geology map is basically a representation of what the materials are just a few feet below the soil. Those are mostly glacial materials. So we'll talk a little bit about both those today, the data, the glacial materials, and the bedrock. And then the fourth product is what's called a bedrock topography map, or basically a thickness difference from the land surface to where the bedrock starts, and sort of a calculated map of where those overlying materials are thickest on top of bedrock versus where they're thin. Other county geologic atlases, I should say, have several different products, an actual quaternary stratigraphy map, which is the different layers of the till bodies, but because, as you will know or maybe already aware, there's very little glacial material to cover the bedrock in Houston County, so those were not part of this atlas. And atlases in general are a comprehensive package of those maps, but also the GIS files. So if you're a county staff or other maybe consultant on the line, if you're interested in the GIS files, those are all available in that same place as you can get the PDFs of the plates. So I didn't have any paper copies of Part A. They do exist. You can buy them online through our website or by calling us and doing it over the phone. Otherwise, they're all accessible online and computer PDF files. So in general, CGAs, they provide information about the distribution of Earth's materials in the subsurface, and they're useful for land use planning and resource management. And they're valued by counties, state agencies, federal agencies, consultants, researchers, citizens, drillers, and so on. Here's where we're at status-wise from this year. In red are all completed atlases, and in yellow are the areas we are working currently, and in white we have not started those products yet. But as you can see, most of southeast Minnesota is very well covered now by updated geologic maps of the area, of the region. So the first thing I want to make clear or describe or define is glacial sediments versus bedrock, right? In most places in the state, underneath our feet, there's a few feet of soil, and then that's followed by layers of glacial sediment, and then the hard bedrock beneath that. Glacial sediment is that loose sediment eroded or deposited by glaciers that consists of a mix of material, right, of sand, silt, clay, boulders. Whereas bedrock is that consolidated rock exposed at the land surface or underlying that other sediment. And of course, they both can host minerals, groundwater. The materials can protect the underlying aquifers. They can affect how we build roads and building construction on top of them. And they're useful themselves for building material, aggregate, and sand and gravel. So it's important to know where our resources are, right? That's why we continue to get mapping funding across the state. So let's get this off our chest right away. We've got the driftless area, right? Houston County is, let's see if this works. There we go. Houston County is right here. This region is sometimes referred to as the driftless area, but really the true driftless area is this one. We don't quite make it in Minnesota, right? And we'll talk a little bit about that in a minute. Drift is just a term we use to group all materials of glacial origin together. So sand, gravel, silt, or till. And as I just said, the term is not exactly appropriate for Minnesota, the term driftless, since we do in Houston County and other areas around it have deposits of windblown glacial material called loess, colluvium, and terraced glacial materials, terraced sands in the valleys from glacial outwash. Since all those can be found in southeast Minnesota, the term driftless isn't exactly appropriate. So we do have record of glaciers moving through here. And I'll touch on that a little bit further in a minute. But in general, that material is 50 feet or less. That overlying glacial sediment is 50 feet or less in Houston County, except within the deep valleys where it has since filled in deeper. I'll show you another map about that. So stepping out regionally, here we are again. Most of the material at the surface is bedrock residuum or weathered bedrock material and that wind-blown loess. Although we can find glacial outwash glacial erratics, glacial windblown bluffs, until patchily in the area within and outside of Houston County. In general, the data that goes into a glacial map are a few different things. The soil map is heavily used by the NRCS. We also use the wetlands inventory map to map out where the organic rich material and peat is. We also look heavily at the enhanced digital elevation map of just the land surface to see if there's any glacial landforms that we can note by looking at those enhanced digital maps of the land surface. We do a variety of field work, excavations, gravel pits, construction sites, and road cuts. And we have a shallow auger soil drill that goes down about 15 feet. And there's 62 new borings that were done across the county to help map those superficial glacial sediments. And we also heavily rely on the county well index and data from water well drilling records. So all that kind of data goes into a geologic map. Here's the superficial map, or plate 2 of the part A county geologic atlas. It is mostly one unit. That's this residuum unit, or weathered bedrock. Bedrock is not weathered, but directly at the surface, anywhere where it's blue. The modern river sediment and or peat is in this bright yellow. So that's in the Root River and Mississippi rivers valleys. And then the variety of other glacial sediment that we have are alluvial terrace sediment, glacial sediment, and colluvium and loess. And those are those colors that are kind of usually, the colluvium, for instance, is along hill slopes, and the QAT, or the terrace deposits, are kind of along the sides of those larger river valleys, and so on. And this is that map that represents just the first few feet below the soil, what exists there. And if you want to know more about those individual map units and textures, that's further described on plate 3. So touching back on that glacial history, this part of the state, all of Houston County included, has not been directly impacted or ice ridden over it since prior to 2,000 years ago. So that's why we still call it the pseudo driftless. But we do have evidence when that glacial ice was very close to Houston County, right, from the glass glaciation. And that's as large glacial lakes formed and drained through Mississippi River and river valleys. We can see evidence of periglacial climate through widespread permafrost and those colluvium layers and so on. So we have evidence that glaciers were nearby, but just ice did not ride over the top of us. And that's unique compared to all other parts of the state. Here's that bedrock topography map, or basically the thickness of where the glacial materials are the thickest versus the thinnest. It's in 50-foot increments. So as you can see, the Mississippi River Valley has the thickest amount of sediment, as well as the root, sort of those deeper purples that represent areas where there's over 200 feet of sediment on top of the bedrock. And then, of course, that large swath of yellow, I guess that goes back and forth, is where sediment on top of the bedrock is 50 feet or less. And that's, important for land use decisions and county rules, I'm assuming, as well. Excuse me. So getting into the bedrock geology now. The bedrock geology is what we call Paleozoic rocks. They're flat-lying, thin relatively, and widespread across all of southeast Minnesota. So as you can see on this map, there's several different ages of rock. Northern Minnesota is that hard, igneous, metamorphic rocks. Paleozoic ocean marine sediments, seas came up, deposited the rock that we have in this region. And the oldest ones are represented by the yellow, or the deepest, those are Cambrian age rock, about 500 million years old. And those are mostly dominated by sandstones and fine-grained shales and fine sandstones. And above that, we've got our Ordovician rocks in the light blue. That's where the start of those is, that tan the tan hard cliffs of the Prairie du Chien unit. So most of the Ordovician rocks are what we call carbonate or limestone or dolomite. And they were deposited, based on the fossils and other things we've studied about these rocks and seen, they were deposited when sea level was much higher, and we had beautiful oceanfront property in Minnesota a long time ago, and it kind of represents a shoreline like you would have, like you're familiar with today on the coast, where the closest to the shore, you'd have the coarsest, sandiest, nicest beach sand. Further out from that is where the shales and the muds like to flocculate and be deposited, and even further off of that, away from all that wave vegetation, is where the sea life is the happiest, and carbonate is actually formed. So it's a matter of, as sea level rise and fall, that's kind of what leaves us with our geologic record and our stack of rocks that we have today. The bedrock characteristics, of course, are different whether you're in a sandstone, a shale, or a carbonate. Sandstones on this column are in yellow. The browns are the finer grained units that are generally more of a protector. And then the carbonate is in this light green that hopefully you can see. So in general, if you look at them from an outcrop scale versus up close, you can start to see some of those differences in the rock properties. Sandstone make great aquifers, right? They have high pore spaces between the sand grains and high connection of pores. So water flows through them very nicely. Versus a shale where the particles are more like clay, stacked up on top of each other and compacted. Those have lower porosity, lower permeability, and they're more of the protecting and the confining units and the protectors for our aquifers. Moving beyond that, limestone can kind of go both ways. Up close on a hand sample, it's relatively impermeous. It's a crystalline rock, but if you take a step back, it's high because it's so hard, it's brittle, it fractures very well, and at a large regional scale, it actually makes it for a great aquifer because of all the fractures. So that data that goes into a bedrock geology map is relatively similar to the data I already went over with the glacial materials. We also look at the digital elevation model of the land surface. We survey all the bedrocks, outcrops in the area, all the road cuts, just for identification. And we also use those Gettings borings in case some of them did reach bedrock. We heavily rely on County Well Index and drillers' descriptions. We also have a variety of drill cutting sets that we preserve at the MGS that we consult, and gamma ray geophysical logs we have, and I'll touch on that in a little bit. We have a variety of a core, and we also use a few other geophysical equipment, one called a passive seismic recording that can basically be a geophysical measurement of the depth to bedrock. So that's been done in a few areas in the county as well. So here's the geologic map for Houston County and what that looks like. You can see we have a variety of map units from the Ordovician on down to the Cambrian. The upper Ordovician rocks are the Cummingsville, the Decorah. Those are only found in this part of the very furthest southwest part of the county. We've got, then St. Platteville and St. Peter in that area as well. You can see most of the blues. The darker blue is the Shakopee Formation, and the lighter blue is the Oneota, and those are both part of the Prairie du Chien group. So that represents the majority of uppermost bedrock across the county. And deep in those river valleys are where we start to see Jordan exposed on the hillside, and the units below the Jordan sandstone, which are the St. Lawrence and the Tunnel City, or the Lone Rock. The Tunnel City is a group, the Lone Rock's within it. So we do a variety of different cross sections across the county. Now I'm trying to remember where these are. This is B to B. This is the lower one. So you can see for the most part, these rocks are fairly flat lying. Yeah, 8A, now I can see it. There's that line right there. So this is a north-south cross section. This is the east-west. And you can see there are some faults that cross the map. And we'll talk more about those in a bit. But in general, flat lying, but there is some minor faulting and folding. Oh, talk about that now. So the way we recognize those faults and folds are by looking at the particular top of a unit called the Jordan sandstone, right? It's well recognized. It's described well on drilling logs. It's a good unit to pick. It differs heavily from the Oneota dolomite above. So it's a good one. It's where that we have quite a bit of data. The Jordan's also a heavily used aquifer, so there's a lot of wells that go into it. And so what's produced is just a hand contoured map of the top of that unit. And through making that, you can find where there's some wells that maybe are near a fault on either side, where the Jordan is, you know, a couple 50 feet to a couple 100 feet lower over here versus here. And that does occur across the county, like in that zone there. They're relatively hard to find in terms of looking at a beautiful fault in an outcrop, despite how much outcrop we have in the county. Here's one of them near County 9, where the beds are all of a sudden somewhat flat lying. I know it's a terrible picture of it. I could use a drone to get a better one. But and then all of a sudden you get to this valley and they kind of steeply dip off in this direction. So that's up near here and in an area where we've got some structure or movement and some faulting nearby. This is also on the map itself. This is just a geologic strat column that further describes each of the units, sort of their relative thickness across the county is written along this edge. This is a geophysical log of the different units, and a geophysical log is a really great way to pair with a cutting set, or even just kind of know where you're at in terms of the stratigraphy. Certain units have a very obvious pattern to them that you can use to correlate from place to place. Shales in general, if you have a higher gamma signature, higher peak, that's going to be a unit with a lot more shale in it than a sandstone, or which is predominantly all quartz. Those have generally lower signatures. Yes, go ahead. Yeah, sorry, that's what that means. This is the uppermost unit down to the St. Lawrence, and then I had to cut it, right, to show it all in one slide, and then it starts here and goes back down. Yeah. So I'm just going to go through some. Oh, I actually also want to say one more thing. Each of these units also, in addition to the geophysical log, I've got this sort of colored pattern of browns and blues. And that represents what we call the hydrostratigraphic properties again, or, you know, blues for aquifer-like units and browns for more confining units. So, you know, Mount Simon sandstone is mostly blue. It's got these little brown hatches where we note that there may be shale in the rock, because some of these units are not all sand or not all shale. They're kind of a mix of both, right? The Eau Claire formation is predominantly shale. So we represent that as an aquitard. And then the Wanawak, mostly all sand, so that's represented in blue. And these patterns here, these squiggly black lines that go across, those are where we've noted a high amount of horizontal fractures or bedding planes, where water actually is known to move horizontally in those areas.
For example, that would be the center on the right of that column. All those squiggly lines in the blue. Is that right? Or?
Yep, exactly.
Okay.
Yeah, sorry, I know they're blown up a little bit bigger on my next slides. But yes, for example, within the Prairie du Chien group, the Oneota dolomite and the Shakopee, that middle zone is actually a well-known zone we refer to as a high transmissivity zone, or a zone where there's a lot of horizontal flow in that aquifer at that layer. So that's why these squiggly lines are schematic in this figure, but that's why there a lot of them are right there.
What's the title on the last column? I can't.
So this is just a split.
No,
so
on the last column of each, the title.
oh, sorry. Yep.
What is
Thickness.
Thickness. Thank you.
Yes. So if you went to find the PDF, all of this will look much more clear on the map itself. Sorry, I know they don't come across all that well sometimes on these images. Maybe these will be, that's probably not even all that much better. But I'm just going to step through a couple of these formations and get to the end here, and then John will finish up. And John will talk a lot more about defining the aquifers and their properties and all the characteristics of them and their you know, chemistries and things and so on. So the uppermost unit that's found in Houston County is right here. It's called the Cummingsville Formation. It's a limestone and it's mixed with shale. So here's an example of it in core. You can kind of see the lighter limestone units, and the more shalier is the darker units. This is an example of core from the Decorah shale. the Decorah Shale, great confining unit, right? It's only about 45 feet thick or so, 30, closer to 35 in Houston County, but makes a great confining unit. Although in Houston County, it is limited to just right in this area. Moving down below the Decorah, we've got the Platteville Formation. So the Platteville is the small limestone about 30 feet thick that sits above the St. Peter sandstone. And as well, these units, about 30 to 35 feet thick, and the St. Peter is about 70 to 90 feet thick, but they are just within that southwest area of Houston County. The Prairie du Chien, that represents the majority of the uppermost bedrock across Houston County in blues. Here's an example. It's a dominant quarrying rock in Houston County. You've likely seen this all over, right? This is maybe easy enough for you to see, but this is a quarry where it's the Oneota on the bottom and the Shakopee on top, and this zone in the middle is where maybe you can see these holes in the rock itself. It approximates the contact between the two units, and that is part of that high transmissivity zone, or where there's a lot of open pore space and fractures, and water travels horizontally in those areas. Not in this image itself where there's no water, but if it was down underground beneath the water table. Here's those two units again in core. The Shakopee is the uppermost unit, the darker blue, and it is a lot more sandy. It's a carbonate, but it's mixed with sand and shale. Whereas the Oneota is going to be a bit more massive and blocky in outcrop, and it's going to have a lot more sort of these bugs or these holes, and it does not have interbedded sandstone within it. Okay. Moving through these, below the Prairie du Chien, we've got the Jordan sandstone, which you're all familiar with. It's a nice sandstone units, anywhere between about 80 and 100 feet thick across the county. It's that white beach sand. You can scrape away at it. It's not barely cemented at all, and represents those tan white sandy cliffs you see across the county. And I guess in general, it is represented by the yellow color. So it's mostly within the valleys and valley walls. Beneath the Jordan, we have the St. Lawrence Formation. The St. Lawrence is a unit that we draw as brown, a confining unit, but it does have a lot of horizontal and fracture flow. It's a unit that has carbonate cement, but the material itself is mostly a fine-grained sand to shale. And then the Lone Rock Formation below that, here's a nice Lone Rock outcrop near Reno, Minnesota. You can see all the beautiful Lone Rock colors. It's a green, sandy sandstone. So if you pick it up, it kind of looks like salt and pepper. It's going to have those blacks to green grains, and that's a mineral called glauconite. And then it's also going to have quartz sand, but it's finer than, say, the Jordan. It's a very fine to fine-grained sand. Green. So here's some of those units in core, excuse me. The St. Lawrence, you can see, is a little bit more cemented, held together by carbonate cement. The Lone Rock is a little bit more sandy. I know those probably aren't coming through very well. And then as you move even further west, the unit below, or further east, sorry, can't talk, right. Got my directions screwed up. That's where we get into the sandy sandstone unit, the Wanawak below that. So these are just representing, just want to show you a few pictures of all the different geologic units, the St. Lawrence, the Lone Rock, and the Wanawak sandstone below that. In general, I guess footage-wise, since you probably can't read it, the St. Lawrence is around 60 to 70 feet thick. The Lone Rock is kind of a consistent 135, 150 feet thick. And the Wanawak can vary between about 110 to 130 feet thick. You'll see the Wanawak, like if you're driving along the Mississippi River Valley, And you're seeing the sand up through here. Those are going to be Wanawak sandstone outcrops. But say if you're kind of coming up through, you know, the higher bluffs, those are going to be Jordan outcrops. But pretty hard to tell the difference between the two units if you just have one small sample.
The formation has the lead.
The lead? The what? Well, that actually can be in several different parts of the formation. So the lead is a hydrothermal system that came through, we believe, back in Permian time. So after these rocks were deposited, kind of sitting there for a couple 100 million years, then hot fluid from all the way down in like Illinois kind of came up through this region, and that hot briny fluid carried lead zinc with it. And the lead zinc crystals are sometimes found within bugs in some of these units. So I believe it's found in the Prairie du Chien. I've seen it found in the Platteville. I don't know if it just wasn't, it wasn't, I mean, it's thought to have kind of come through all of the units up to a certain point into Minnesota, but for some reason it's really just, it seems to be better preserved in those limestone units. Second to last slide here. Hopefully I'm doing okay on time. I have no sense. Okay. I don't have my watch on today. Moving below that, we've got below the Wanawak sandstone, we have the Eau Claire formation. Again, oops, sorry, this is an outcrop of the Wanawak sandstone. The Eau Claire is barely found kind of in this region up near Dresbach. It's very sandy in its uppermost section, so I didn't have a great picture of it at that spot. This is further up in Wabasha County where you'll see Eau Claire, sort of thin bedded, silty, fine grained shale and siltstone. Yeah, I guess, and in terms of thickness, the Eau Claire, we've got about 115 to 150 feet thick. And the Mount Simon sand below that is not exposed in the county, so I don't have a picture of it for you. That's our thickest unit, from 300 to 350 feet thick. The Mount Simon is at the surface through the Mississippi River Valley. I mean, it represents the uppermost bedrock, but there's plenty of quaternary material that's covering it on top of it. So just wanted to touch on this before we get into John's work. The hydrostratigraphic model is what we call this. This represents a cross section or a slice across all the way over from Malheur County, Fillmore County area to Houston County over here. So the geology in Houston County, the geologic setting is very different than, well, it's not exactly the same, right, from here to over in Malheur County. The geologic units exposed here are older and deeper, right? You get a sense from that tilting of the rock that at the surface in Houston County, we're getting the deepest Paleozoic bedrock exposed at the surface and in these deeply dissected valleys. But the rock at the very top is still the Prairie du Chien at this very uppermost surface. But say if you were in Fillmore County, only part of it is Prairie du Chien. Then you've got a lot of that galena on top of that. That's much younger. The other thing I wanted to say is, so again, just reiterating, different rocks behave as either an aquifer or an aquitard based on their texture, right? Based on their properties. Sandstone transmits water very readily through large, well-connected pores. And so that's represented by blue units. Sorry, that blue color didn't come out very clearly. But the blue units through here are the aquifers units. The shale, siltstone, and fine grain units are the ones that provide hydraulic confinement because it's harder for water to move through those units. And the pore spaces are more poorly connected. So that is represented in the browns. So if you've got a well, you know, and on your property, you're likely in one of the blue areas, right? You've got to go through a unit that doesn't have a lot of water flow into another one, into the aquifer. But we are fortunate in Minnesota to have a large stack of different units to work with, right? That is not the case everywhere. And then I did want to touch on another thing, that all all units, whether they're a shale, an aquitard, or a aquifer, they can all have fractures and conduits, right? Both vertical and horizontal, and those greatly enhance the rock's ability to transmit water. And they are most abundant in what we call the uppermost 50-foot zone. And that is sort of shown on here, hope maybe you can see, is that the uppermost 50 feet, kind of this far, it has a lot more enhanced fractured on this schematic image. So whether you are an aquifer or an aquitard, if you're in the uppermost 50 feet, anything kind of goes. And then John's going to talk a lot more about this. I didn't mention it yet, but carbonate rocks, right? They are CaCO3, calcium carbonate. They dissolve weakly with a natural acid like rainwater. And so that produces dissolution, and that produces karst. And so carbonate units like the big carbonate units like the Prairie du Chien, and then you have a little bit of Platteville and Cummingsville. Those are the units that are going to have the most dissolution and likely the most karst features. But all units, because they can all have fractures, can be associated with enhanced flow and permeability. Yes.
So I know we're going to hear more about like the flow of water, but on this map, it looks like there's some blue arrows up there, kind of pointing either left or to right. I'm assuming those are related to the flow.
Yes,
And
exactly.
So in our area, we're not really seeing a lot of flow coming in from way over on the western side of this schematic.
Yeah, it's an east-west schematic. So in general, you're right. In general, flow is going in this direction towards the Mississippi River. That's the biggest, area where water wants to go to. But if you are, say, it's hard to think because we're not always in three-dimensional space, right? If you are here, water's going to want to go that way. But if you are like right here on one of these edges, that's where, water's going to want to go to the tributary before it goes to the Mississippi. So it kind of depends on where you are. It's going to always, water's always going to take that path of least resistance and either go to a tributary that eventually is going to go to the Mississippi, or it's going to try to cross-cut those if it can and just go right to the Mississippi.
But on that one map,
Yeah.
inside those different layers, we're seeing kind of a western flow over there, say the Decorah and then Galena group, or that Prairie du Chien group. You're seeing things moving to the left of this map.
Right there.
Or further over to the west.
Or over.
We are on the left side.
Okay.
Yeah.
Yes.
So that water is not technically coming our way in a sense. So whatever's going on in, say, nitrates or any other kind of filtration going through the system, it's more likely not coming into this part of the county.
Right. Sort of Malheur, I believe that is the interpretation. Sort of when you're way over in Malheur County, it's got to go through rocks that are going way up in slope, and it's far enough away from that draw of the Mississippi where the flow is going to go more west or south. Yeah. But across Fillmore County, for the most part, I believe it is to the east. Somebody else have a question?
So you see on the log, you see Franconia for a big well.
Yeah.
Okay, to talk about
Yeah,
that.
so exactly. I didn't talk about that. So it wasn't, that long ago, but I was still at the survey right when we changed all the names. So the Franconia is a name that Minnesota has used for a long time, the Franconia Formation. But Wisconsin was calling it a different name for the same unit, and that got confusing, right? So Wisconsin won the battle. And we now call the Franconia Formation the Lone Rock Formation. And again, it's a little bit even more confusing because we have the Tunnel City Group, and the Lone Rock's a part of that. In Houston County, the Tunnel City Group only has the Lone Rock Formation. If you were in Washington County in the North Metro, you'd have both a Mazamani name and a Lone Rock name, all part of the Tunnel City Group. So not to confuse you, but yes, we have some older names in the system, as well as the Ironton Galesville that is now represented by the name the Wanawak Sandstone. So just to be consistent with our neighbors, it's probably something we should have done many years ago before 2008, but in 2008 we finally now have consistent names with our neighbors. And I believe those are the two big ones. Yeah. Happy to take a question if there's time, if there's any others. Otherwise, we can always take them at the end after John talks too.
Okay, folks, we can start the second half of the presentation here. My name is John Barry. I'm a hydrologist at the Minnesota DNR, and I work in the Groundwater Atlas group. And so what we do is we follow the work that the Minnesota Geological Survey does. They do the geologic mapping, and then we go back and collect water samples to determine the pollution sensitivity of aquifers and the natural chemistry of aquifers. And so the rock itself is the container for the water. And so we start our work after that Part A mapping is done. And so I'm going to sit down here. That way, the people that are online can see my cursor as well, when I'm pointing to things. And so just want to acknowledge that our funding is also through the LCCMR, the Environmental Natural Trust Fund, and the Clean Water Land and Legacy Act. So County Atlas series, it's actually two parts. So Julia just presented on Part A. The Part A is the geologic portion, and then the Part B is the groundwater atlas portion. And so one atlas really has two parts to it, the geology and the groundwater. And so just like Julia did, she showed you how to access products and how much mapping's been done. You would get our groundwater atlas products through the Minnesota DNR webpage. You could do a Google search to Groundwater Atlas Minnesota, and that would get you there. The map that we are currently at, our status map, the areas in dark blue is where we have a completed groundwater atlas. So we are currently working on Olmsted County and Dakota County, and Steele County. And once we're done those, we'll technically have all southeastern Minnesota covered for the groundwater atlas portion. My cursor to the side here. So again, how would you get a groundwater atlas? You could just do a general Google search for Minnesota DNR groundwater atlas. That would get you to the page that you see in the block box there, the groundwater atlas program. And if you click on that, it would open our web page, and you would see the groundwater atlas icon. And below that, you'll see the map that I just showed you, the dark blue areas where things are completed, and that would get you to the actual County Geologic Atlas series. There you would find links to the Part A's, so the map that Julia just presented, the geology itself, and then also it would get you to the groundwater atlas. So for instance, H, if you clicked on H, you could scroll down, Hennepin's above it, and then Houston County. And so you could see that Part A geology, there's a hyperlink there in blue, and then below it, Part B, groundwater hydrogeology, there's links to each of the products. So what are the products? Well, the products are what are in the paper envelopes from when you walked in the room. So you don't need to go online if you don't want to, because you have paper products that you can bring home. And so everything that you would access online is available in this orange packet. And then for those of you online, I'm presenting some digital links real quickly. So if you wanted the report, you could click on that link. The water chemistry plates. And when I use that word plate, plate means the map. So the maps in this packet are really large maps that you fold open. Those are referred to plates. So plate 5 would be the water chemistry, where we collected water chemistry samples. And plate 6 are hydrogeologic cross sections. So similar to what Julia showed you earlier, it's that same idea, but from a hydrogeologic perspective. Okay, so the Houston County Groundwater Atlas, it consists of the report itself. So the report is, I don't remember the number of pages offhand, but that's what you would find in the booklet in your packet. And so not every slide that's in the report, not every figure that's in the report is included in the slide in this presentation. So I'm going to skip over some just because some of them would be redundant. We'll just kind of hit the key figures. So those are the elements and the bullets that are in the report. So groundwater flow, water chemistry, pollution sensitivity, and then we also present groundwater use for permitted wells. The plates, we just went over that, water chemistry or hydrogeologic cross sections. And then the links that I just provided on the previous slide would get you to those same things if you didn't have a paper copy. So if you were online, for instance, it could get you to the report, the plates, but it also gets you to GIS files. GIS is an acronym. It stands for Geographic Information Systems, and that's a software tool that we use to create these figures. So a lot of consultants or county folks would want to access those when they're doing analysis. And so those files are available through our website. So in addition to creating these groundwater atlas reports, these Part Bs, the program that I'm in does other groundwater work in Minnesota statewide. And so we have a databases of springs and spring sheds in Karst. Karst is a term that has already come up, but we'll get into it in a little bit more detail shortly. We also have something called hydrogeology atlases. And so, for instance, the figure that you're looking at in the lower left right now is the near surface pollution sensitivity, so statewide. And so those colors represent how sensitive the aquifers and near surface aquifers, so shallow water table aquifers, primarily aquifers that are it's aquifers that are within 10 feet of the land surface. So it lets you know whether human impacts on the land surface may be moving quickly to the water table based on the texture. And texture was a term that Julia mentioned earlier. Texture just means like whether it's sand or clay or silt. And so water moves differently through those materials. So water would move more quickly through sand than it would through clay, for instance. Another product that we have is the groundwater provinces. And so that's a way to basically lump regionally how groundwater resources behave or how they are available. And so you'll see, I think there's 6 areas. The number 3, the orange in the southeast here, is the Karst area. And we're going to talk about Karst pretty shortly here. Elsewhere in the state, so for instance, the dark green in the west, that's really clay area. And so there's not a lot of water available. It takes a long time for precipitation to move through clay. There's not a lot of broad sandy aquifers that are buried. And so accessing water in that dark green number 5 is a lot more difficult than like in number 1 or number 3. Up in the Arrowhead, the number 6, that's mostly crystalline rock. If you've ever been up to the, Lake Superior, those rocks are basically crystalline rocks, and there's just not a lot of water in that rock. And then lastly, a product that our program used to work on before we kind of got into the groove we're in now are called regional hydrogeologic assessments. It's very similar to what we do now, but it was multiple counties at a time. And so now we do it a little bit more focused at a county at a time. That gives us better resolution, more data per county, et cetera. But all those resources are available through that same groundwater atlas page that I showed you before. So let's do really quick groundwater basics, some terminology. So groundwater. Now, what is groundwater? It is water that's underground, right? It's water that's below the land surface, and it can be used for extraction for wells, for drinking water. It could be used for extraction for irrigation. It could be coming out of a spring. So it's water that's below the land surface. Aquifers. What are aquifers? Aquifers are underground layers of water. And so there's different types of aquifers. There's unconsolidated, like a sand aquifer, or there are aquifers that are bedrock aquifers. And Julia kind of painted the picture that bedrock is really what's available in Houston County. And so most aquifers in Houston County are bedrock aquifers. And basically an aquifer, you can basically extract water from that unit. So whether it's bedrock or sand, there's enough water there that it can be extracted via a well for use. Kind of like the opposite, not the exact opposite, but an aquitard. You can get water easily out of an aquifer. Aquitards limit the movement of water. And so Julia described different hydrostratigraphic attributes earlier. And so she, talked about bedrock that's within 50 feet of the land surface might be fractured or dissolved a little bit because it's karst and carbonate. That would be a good aquifer. The sandstone was a good aquifer. But then she also highlighted shale units. So the St. More shaly units, some siltstones like the St. Lawrence or the Eau Claire, and those are aquitards. They slow down the movement of water, is certainly in a vertical sense. Now, sometimes water can be moving on little beds in between it quite rapidly. So it's a little bit of a conundrum of sorts. It's like, well, water's moving very slowly in a vertical sense, but it moves quickly. And an example of that in Houston County or Winona County are a lot of the springs. So if you're in the deep valleys in eastern Houston County, there's a lot of springs, right? A lot of trout streams in those areas. And it's kind of odd, but a lot of those springs are coming out of the St. Lawrence unit. And so it's aquitard if you're like in Caledonia, away from a bluff's edge. It's a very competent aquitard. But in a valley setting where it's been eroded, in that area, it may actually have a lot of water moving through it horizontally. So I just wanted to point that out. So another thing we talk about with groundwater is residence time. And residence time is basically a way of describing how long does it take water to move from the land surface and to the aquifer of interest. And so that also just really depends on how deep's the aquifer of interest, right? And so if you have a shallow, unconfined aquifer, so like something in a river valley, the Root River Valley or the Mississippi River Valley, water could take just like days or years, right? If it came down as precipitation, whether it be rain or snow, it wouldn't take very long to move to where it's discharging. And so it would be discharging to the Root River, for instance, or to the Mississippi River, depending on where you are. And so that residence time can be very short versus if you're deeper into the Lone Rock that she was talking about. That was much deeper, or the Mount Simon, for instance. So, the Lone Rock may be decades to centuries, whereas when you're in the Mount Simon aquifer, water can be literally 10,000 or more years old. And I'll show you examples of that later in this presentation. So let's get into actually some of the figures in the report itself and just talk about them briefly. So the way this is set up is that the chapters within the report itself, we've kind of compartmentalized those in the presentation, but for specific figures, it'll tell you which page of the report and which figure number it is. And that way, if you want to follow along, or have questions some other time and want to reach out and contact me, we'll know exactly what you were talking about or what to dial in on with respect to your question. And so Julia touched on this already, but it is quite important. And so the driftless area, right? And so the inset on this figure is not in the report, but it really does kind of impact the way groundwater flows in Houston County and elsewhere in southeastern Minnesota. And it's the driftless area. It's that really mature landscape that's been heavily eroded from glacial meltwater. And what you'll see if you move kind of from Mower County or to the east is that there are plateaus, and plateaus mean just kind of like generally flat areas of the landscape. Now, if you're driving out there today, for instance, it's not flat like a cornfield in Nebraska, but it's flat relative to the relief like in La Crescent to where we are in Caledonia, right? So it is a rolling landscape, for instance, but it's on similar elevations. So far to the west of us, and reaching into the Spring Grove region, that area that Julia showed earlier with the Cummingsville and Platteville and Glenwood and St. Peter, that upper carbonate plateau just touches Houston County right in that little corner. East of that, where we are now in Caledonia, is something called the Prairie du Chien Plateau. And the word Prairie du Chien, that name should sound familiar by now. That was the dark blue and the light blue that Julia was showing in her presentation. So that's that carbonate rock, the dolostone, the limestone that makes the bluff edges. So if you're driving on Highway 61, heading up towards, Red Wing or something, that's that kind of steep, bluff edge that you see. And so, and then the green areas on this map represent just like where all that stuff has been eroded away, right? This glacial meltwater came through in torrents for tens of thousands of years and eroded through these rocks. And so the deep valleys are kind of the last of that geologic setting. And the geologic setting really influences how water moves through the rocks and really like what we do down here, right? Like the Prairie du Chien Plateau, the Upper Carbonate Plateau, fantastic farming areas, right? Like it's relatively flat, there's some soil. It's not, the depth of bedrock shallow, but there is soil available, et cetera. So it impacts how we use the landscape as humans, but also how water moves through that landscape. So yeah, the driftless area, regional scale plateaus and deep valleys. So bedrock, Julia touched on this already, so a little bit of overlap, dolostone, limestone, think of the Prairie du Chien unit, sandstone, think of the Jordan unit that you start to see in the valleys as you move down towards the river levels, and then siltstone, kind of those thinner units in between that showed up as the color brown for the most part on Julia's stratigraphic columns. And so the key point, and Julia touched on this, thank you, Julia, is that the rock composition and also how much fracturing is in that rock really determines whether a rock or a rock unit is an aquifer or an aquitard. And so, a sandstone, it could have a lot of pore space and would be an aquifer, and a siltstone would have very little pore space, or a shale would have very little pore space and would limit water moving through it. And so that's how that coloring got completed on her maps, and that those maps will look very familiar to you shortly. Now, Karst has come up, and Julia touched on it nicely. This is actually a picture of a sinkhole over near Spring Grove with water flowing into it after a rainstorm. But Karst is basically both a landform and a hydrology term that describes where water can move quickly through a landscape. There's turbulent flow, and it was created by the dissolution of the rock itself. And so the rock is soluble; it can dissolve. And so over time, those fractures get larger and larger. And like key examples, would be just west of here in Fillmore County, right? You could go to Niagara Cave near Harmony. You could go to Mystery Cave or over near Wyckoff. You are literally walking through an aquifer at that point. There's water dripping, there's water moving through the channels. And so you're literally walking through an aquifer. So the development of the karst really depends on the rock units. That rock unit is kind of different than what we have here in Houston County, other than that small little portion in Spring Grove. And so the key point is that karst, you can have very rapid connection between the land surface and aquifers below. And another key point is sometimes people say, well, I don't have a sinkhole on my property, so I don't have karst. And that's really kind of a queasy argument, because karst is the system itself, not just the presence of a single sinkhole or sinking stream. So how is karst formed? Julia touched on this. Water, precipitation, whether it be rain or snow, falls. It picks up carbon dioxide either from the atmosphere itself or from the soil horizon, and it forms something called carbonic acid, just a weak acid. Acid etches away at the rock itself, limestone, and it frees up into these. So through that process, you've dissolved the rock. And so examples of karst in Minnesota, the map on the left, pardon me, shows areas that are kind of in a red, hot pink color. And you'll see that most of southeastern Minnesota shows karst, where karst is prone. You will see a little bit north of that up in Pine County. That's a very specific type of karst called a sandstone karst, which is a little bit different. So we'll stay focused on the karst that's down here in Houston County and as part of the story in Houston County. But karst, it may look like sinkholes. Certainly springs are part of karst systems. Sinking streams, you do have those in valleys down here. I would imagine most of you are property owners down here. If some of you live in valleys, you'll know about, or you'll have heard about it from neighbors. Water actually is flowing down the valley and then disappears, and then it comes up at a spring elsewhere. So as part of the project many years ago, we introduced some natural organic dyes that allow us to trace where that water goes and also determine how quickly that water is flowing. Caves, that's more of an example for what you have in Fillmore County than here, although there are some kind of at that contact between the Shakopee and Oneota that Julia was mentioning earlier. And then lastly, just enlarged fractures. So here you know, it may be a mechanical fracture initially, you know, where the rock kind of broke apart, but over time, water is moving through that and making that fracture larger. And so you can imagine water, you know, that fell as rain or precipitation, rain or snow would move very quickly in a vertical sense through that, bypassing that rock that's there on either side of it. So we have that map, an area prone to karst feature development. And so how do we create that? We use carbonate rock, so the limestone and dolestone as mapped by Julia and others at the MGS. And so that's where carbonate rock is within 50 feet of the land surface. And so this map looks very similar to the map that Julia showed with that, I think it was yellow, wasn't it, Julia? The depth of bedrock. And so and that's because you've got carbonate rock within 50 feet of the land surface. So, you know, if the stratigraphy was a little bit different, you might have more holes in it. And so imprinted on top of that are springs in blue, sinkholes as those red X's, and then sinking streams. And I just acknowledged sinking streams. There's not many of them mapped. There's probably a lot more of them that we know about, but, you know, we only learn about these things if, you know, landowners are interested in telling us about them. We can't just access properties, of course. And so that's a key point there, is just that a lot of the surface, that Prairie du Chien Plateau, is prone to karst feature development. And so as a parallel product to the Winona and Houston atlases, there was something called Karst Landscape Unit Mapping. It's a companion report. It's not within this report. You'd be able to find it on our webpage. But it basically just looked at what's the surface. So like there's a karst mesa near Spring Grove. There's a rolling karst, a karst escarpment, and basically 4 of the 5 are either karst or pseudokarst. Pseudokarst means that it can have very fast flow through it, but it's not necessarily from dissolution. It could be just like the rock is fractured, like Julie was mentioning earlier. So really, the only area that wouldn't have potential karst flow in Houston County is really just in the valleys, right, where it's just full of sand and gravel and silt. So just wanted to make you aware of that report. And so one way we looked at karst in Houston County was just to map the sinkholes and stream sinks that were available in the county versus depth of bedrock. And what you see here is that nearly all the sinkholes and sinking streams within Houston County are within 50 feet of the land surface. So that's just one way to kind of double check, you know, does that logic make sense? Like, is mapping the area prone to karst feature development within 0 to 50 feet, does that make sense? And when we do this in Houston County, Winona County, or across southeastern Minnesota, we get that same kind of frequency distribution. Most karst features are, you know, anywhere between 0 and 50 feet to bedrock. So Julia showed the stratigraphic column, the hydrostratigraphic column earlier, so you've already been exposed to this. Again, blue on this figure is are aquifers, brown are aquitards. What you'll see next to that are these frequency distributions. So this in red are where are sinkholes located in the county. And you'll see that most sinkholes are in the Prairie du Chien group, and that most of the sinkholes are near that contact, that geologic contact that she talked about earlier. She called it a high transmissivity zone. And so you'll see that most of the contacts form near that high transmissivity zone. And that's the same throughout southeastern Minnesota. Pardon me. You'll also see that most springs in Houston County occur either in that St. Lawrence group or in that Lone Rock group. So these are the headwaters to the trout streams in the eastern portion of the county. And I just wanted to do a quick way, linking like an outcrop, what you would see in nature to an actual stratigraphic column. And so the figure on the right, I just added that dashed line to it. And that's a difference between 2 different geologic units. And so when you're looking at the cross section, that's kind of what we're doing. We're looking at different rock units and symbolizing them in this thing called a stratigraphic column. So just wanted to offer that to you to just kind of link, you know, the natural world to what you're looking at in an image. So the upper portion, this might be familiar to you by now. And so there's the full column. Julia broke it up and had an arrow to the right. I'm doing a little bit different here, but here's the upper portion of it. And again, you'll see that, you know, the sinkhole distribution is primarily within the Prairie du Chien unit. There's a little bit of seepage and a stream sink, but most of the sinkholes are within the Prairie du Chien, and in particular at that Shakopee Oneota contact. If we move a little bit deeper, now we're looking at the lower portion of the section. You'll see that most of the springs, these blue lines, most of them are either at the base of the St. Lawrence Formation or in the Lone Rock Formation, which is also referred to as the Tunnel City, you know, previously known as the Franconia, for that question that came up earlier. So the St. Lawrence Formation, you're going to hear a lot about the St. Lawrence for the rest of this presentation. The St. Lawrence Formation, you'll see that Julia has painted it brown. It's an aquitard in a regional sense. So water cannot move through it very quickly in a vertical sense. But we do get some springs on it, so it can move through it on a horizontal sense. And so the St. Lawrence, there's a picture of it, not here in Houston County, but just to get you acquainted, just this kind of tight, silty bed that water can't move through vertically, but you can see like in that crack there that it could potentially move through horizontally. And so superficial aquifers. There's just really not much water available in the superficial aquifer. It's very thin superficial profile here. The picture there shows, you know, there's just like not a lot of sand and gravel, you know, silt, loess, et cetera, on top of these bedrock units. So they're typically unsaturated and they're typically very thin. However, in the Mississippi River Valley and the Root River Valley, there is, you know, a fair amount of unconsolidated sediment, right? Those glaciers were eroding all that material out of Houston County, but it was also transporting sand and gravel and weathered rock from elsewhere. And so those valleys got filled back in with some of that. And so in these valleys, the little black dots on this figure are wells that, you know, primarily domestic wells, residential wells, where people actually do have wells in sand and gravel. But the majority of the county is that area that's in white, you know, elsewhere, that Prairie du Chien Plateau, that region's prone, where there just isn't enough of a saturated, unsaturated materials to extract water from a well. And so here's an example. We're not going to go through every one of these figures. And so here are the water table elevations of the Oneota. And so if you look at the Oneota, it does show up as brown, and so which would be an aquitard. Here I'm saying an aquifer, but on a residential level, it's all scale kind of related. At a regional scale, the Oneota can act as an aquitard, but like on a residential well level, you can very likely, you know, you're pumping at 10 to 12 gallons per minute. You know, you're not, you know, you got a family of 4 or whatever. You can get enough water out of that aquifer to use it. And so we use water table elevations that are available to us through CWI. CWI is an acronym for County Well Index. So anytime a driller puts a well in the county, that we know the location of that well and we know the depth of the well, which aquifer it's in. And so we can use that data to basically interpolate what direction water is flowing, you know, whether there's steep gradients, et cetera. So you're looking here at contours. And this is just kind of like looking at a map if you're going hiking somewhere. You know, the closer the contours are, the steeper something is, like on a topographic map. The same with these. And so water flows perpendicular to a contour. And so we took the liberty of drawing these little arrows to show you flow directions. And so that question earlier was like, what direction's water flowing? Well, in this water table aquifer, so it's bedrock, but it's not confined. It's not underneath an aquitard. Water is flowing towards regional discharge areas. So if you were over near Black Hammer, I think is the name of it, or, you know, over near Beaver Creek Valley, water might be flowing a little bit like to the north or northwest. If you were over near Bridge Creek area, you know, in the western portion of the county, water might be flowing northeast towards the Root River Valley. So in these shallower water tables, it really depends on where you are in the county. Want to point out that once you get a little bit deeper, so into the Jordan Aquifer, there are areas of it that are confined. And that means that it's the water level in those wells would be higher than the elevation of the top of that aquifer. And that lets you know that there's a little bit more protection, for lack of a better term, in that well if it's a confined aquifer. But the same general groundwater flow patterns exist. So the confined portions of the Jordan, in this case, are where you see that stippled pattern. And then so as we get deeper, now we're deeper. This would have been what used to be called the Ironton-Galesville Formation. It's now called the Wanawak. But as we're getting deeper into that stack, this is kind of what you're seeing on when you're on Highway 61, when you're looking right out your window, kind of almost, like right at level looking out the window. So you're much deeper in the aquifer now, and you'll see that the contours are spaced much further apart, right? So you'll also see that the entire aquifer is confined. And so the broad pattern of flow is really east or like towards the root river. So you'll see that there's less of that regional characteristic to it. And along that same idea, if you move into the deepest aquifer in the neighborhood, the Mount Simon, you'll see that same pattern, but even more subdued, right? Nearly all the water's flowing east towards the Mississippi River. You're really deep in the aquifer section, up other than a little bit that's bending towards the Root River, up in the northern portion of the county. And so we get this funding. We have the maps of geology from the Minnesota Geological Survey, and we reach out to well owners so that we can sample their wells or springs for water chemistry to help us determine ultimately the pollution sensitivity of these different aquifers. And so some real quick water chemistry basics. When water hits the land surface as rain or snow, it immediately starts dissolving what's in the soil profile or within the rock below it. And so that happens very quickly, and over time, as that water moves along flow paths, that chemistry changes, right? It's not the same flavor it was when it hit the surface. It's changing its chemistry as it moves along its groundwater flow path. And so those are things to consider as we move through the presentation. And then lastly, just what's dissolved in water, whether it's sampled at a well or a spring, what we find in that water can provide information about the residence time of the water. Residence time, as a reminder, is kind of like how old that water is. When did it hit the landscape before it got to the aquifer of interest? But it also can tell us about, did it fall as precipitation and quickly enter the aquifer, or did it evaporate some first? And it could tell us about the flow paths. Is it changing along certain geochemical profiles as it follows its travel path? And so we sampled in Houston County. This was over near Spring Grove. We were sampling a well, and some goats decided to leave some hoof prints on our vehicle. But we collect water samples. Basically, we have a budget for about 90 samples for most counties. For Houston County, we had a unique circumstance where we were able to get some money through the Department of Fisheries, because they were very interested about spring water and trout streams, and so we were able to have a bigger sampling budget than for most counties. And then we grab water samples that are available from other state agencies too, publicly available data from like Department of Ag or MPCA or Department of Health. And so we run chemical analysis if there are any chemistry geeks, basically major cations, minors, trace metals, but then we also do stable isotopes of oxygen and hydrogen. That can tell us whether or not the water quickly entered the landscape or whether it evaporated some first before it entered the aquifer. And then lastly, we collect for something called tritium. And tritium is our primary tool for determining the residence time of water. And so I'll get into that on a future slide. And then lastly, after we have some tritium samples, if we find dead tritium, basically meaning there isn't elevated tritium in that sample, we go back to 10 other wells and collect a carbon-14 sample. And so tritium will tell us whether water entered the ground, before the 1950s or after the 1950s. Carbon-14 can tell us whether the water entered the ground up to 40,000 years ago. So millennia versus decades. And so real quickly, there's not a whole lot of a stable isotope story, but we're just kind of following along with the report here. What you'll see here is basically most of the samples plotted clustered together as those gray dots. So this trend here. And so off of that, there's a separate plot with just a couple samples. And 2 of those samples are on something called an evaporation line. And so that's that kind of teasing out I was talking about before. So meteoric means that it's rainwater or snowmelt that came down. And if it plots along this line, it means that it quickly entered the aquifer or the landscape. Waters that evaporate are on a different trend. A slope of 5 is what it's referred to. And so those waters basically are subjected to evaporation. Well, it's not a big surprise, quite frankly, that we didn't see much evaporation here because there's not a whole lot of surface water, right? There's not lakes in Houston County. There's not a lot of wetlands in Houston County. So we only found 2 samples. And so where were they? Well, so surprise, surprise, right on the east side of some open water wetlands in Blue Lake and La Crescent. Other than that, we didn't find evaporitic signatures anywhere. But again, that's not a surprise because there's no lakes in the karst, right? Karst, you can't really form a lake in a karst region because there's just too many fractures and dissolution features. You don't hold water on the landscape. That's kind of the take home there. So resonance time, tritium and carbon-14. Why is there a picture of a bomb going off? Well, tritium is a tool that we use and hydrogen bomb testing in the 1950s, kind of peak Cold War, increased the amount of hydrogen in the atmosphere. And so we can use that basically as a tool. Is there tritium present? If there isn't tritium present, well, it's pre-1950s, pre-atomic hydrogen bomb testing. If there's tritium present, well, then it's post-1950. So, this was a really great tool, like in the the 80s and 90s. Well, it's 2026 now, right? And so now this tool is 70 years, so is the water younger than 70 years or older than 70 years? But it's still a very helpful tool, and you'll see that in the pollution sensitivity maps. And so we basically use adjective terms. So modern is water that entered the ground after the 1950s. Pre-modern or mostly pre-modern is prior to the 1950s. But some waters, most groundwaters are mixtures, right? You've got some water coming rapidly through the Prairie du Chien and it's mixing with water in the Jordan that's a little bit older. And so a well like that, you may have a mixture. It's not pre and it's not post, it's a mixture of both. But these are very helpful tools for us to determine residence time, and in particular, pollution sensitivity. And if we couple that with carbon-14 for the waters that are greater than 100 to 40,000 years old, we can really paint a picture of how protected these aquifers are from activities at the landscape. And so we couple residence time indicators, tritium and carbon-14, with, in particular, two things that humans introduce to the landscape. So chloride. Chloride is basically comes from, road salt primarily. We live in Minnesota, of course. We need road salt on the roads to drive safely, but we put a lot of road salt down, and that all ends up in groundwater. You could also get it through water softener salts if you have a water softener at home, and it can also be in potash fertilizers. And so concentrations of chloride naturally, some chloride falls in rain just naturally, but that's less than 5 parts per million. And then we're able to determine whether chloride is from a human cause or from really old chloride that was present in some of these aquifers from when the map that Julia showed, where there were ancient seas, some of that chloride's in some of those deeper aquifers, and we can tease that out using something called a chloride to bromide ratio, and that's all in the report. But the key take home is that anthropogenically elevated chloride that was introduced by humans, is really found primarily in aquifers above that St. Lawrence aquitard. So this is when I'm going to start hammering on the St. Lawrence. The St. Lawrence is a really great protective aquitard down here in Houston County. And so we see chloride in aquifers above it, Prairie du Chien, Jordan primarily. And And but we also see chloride in valley bottoms, right? If you're driving up, 61, that's getting salted, or if you're, in the river valley. So in the bedrock aquifers, it's primarily above the St. Lawrence. This is a really busy map. It's talked about in the report, so figure, not map. But basically, it helps us determine the chloride to bromide ratios and what those breakpoints are. And so for Houston counties, chloride to bromide ratios less than 300 are naturally elevated chloride. And so where do we see that? Primarily in the Mount Simon. And so there's not even a whole lot of Mount Simon wells. So I coupled that together with Mount Simon chemistry from the Department of Health for all southeastern Minnesota. But you'll see that most of the elevated chloride, including concentrations that are quite high, over 100, and remember 5 was the break point. Natural chloride is in the Mount Simon. Other than that, the ones that are the green, these are those mixed signatures. Most of that is chloride that was introduced probably through road salts or water softeners. And so if you look at a map of chloride concentrations, what you'll see is that springs and wells with elevated chloride, so the larger the symbol is, means the more chlorides in it. Most of those elevated chlorides are above that St. Lawrence aquitard. And so that's just like another take home, like that water is getting impacted, and the deeper, older waters are still quite protected. And so that's a take home from that figure. So another anthropogenic indicator is nitrate. And so nitrate basically comes through fertilizers and animal and human waste. So whether it be manure or human waste, through septic systems or fertilizer. And so concentrations greater than 1 part per million are from humans. And so we know that through a bunch of different studies throughout Minnesota and the upper Midwest. And so natural concentrations of nitrate as rain or in groundwater in systems that aren't, like forest systems or prairie systems, the natural concentrations are less than 1. And one thing about nitrate is it's, for lack of a better term, like a canary in the coal mine. If you have elevated nitrate, you often have elevated pesticides. Our program doesn't sample for pesticides, so that is based on work that the Department of Ag has done. But the Dakota County, up towards just south of the metro area, St. Paul area, they have a gigantic database where they've done a lot of sampling of nitrate and pesticides, and they found basically the same result. As you're, up above 3 parts per million, you're likely to find more pesticides and higher concentrations of those pesticides. So I just wanted to bring that out because the question comes up often, so I just thought I would hit on it right now. So distribution of nitrate, kind of similar as the chloride figure earlier. The bigger the symbol, the higher the nitrate. But it's that same story. Elevated nitrate basically is either in spring edges where there's that mixing, in valleys, but it's really in wells above the St. Lawrence aquitard. So, basically the Prairie du Chien and the Jordan. Prairie du Chien's karstic, the water can move through it quickly. That water can move down to the Jordan. And the Jordan, if we look at nitrate over time, the Jordan, which has been done a lot recently through collaborations with Geological Survey, Department of Ag, and others, nitrate in the Jordan aquifer is slowly climbing over time. For Houston County, these are called nitrate box plots. And if you look at the y-axis, that's the concentration of nitrate. And then what we've done is plotted against the plateau, those geomorphic areas that I started off with. So the Prairie du Chien Plateau or deeply incised valleys or the upper carbonate. But it's really that same story. So for bedrock wells above the St. Lawrence, you'll see that there's a wide range of nitrate values, but the median value is 2.5 milligrams per liter. If you look at bedrock wells below the St. Lawrence, it's a tighter spread, but more importantly, the median value is 0.01, almost not even detectable, right? And so here you see again that the St. Lawrence is a really competent aquitard and is doing a great job protecting those deep aquifers in the county. Another way to look at it is kind of that same idea, same logic, but in the deeply incised valleys. So springs at or above the St. Lawrence, median nitrate 6.1 parts per million. where springs below the St. Lawrence, that aquitard, it's 1.84. And so same idea. St. Lawrence is doing a good job. And then in the valleys, some of the wells are sand and gravel wells. Those were the black dots on the figure that I showed you earlier, kind of with the blue. That nitrate value is less than 1. The median nitrate value is less than 1. A little bit of spread to it. But the bedrock wells in those valleys are typically deeper, and those concentrations are quite low. And so you're in those deeper aquifers in that bedrock setting. And so won't spend a whole lot of time on this, but we can plot all the water chemistry into something called a Piper diagram. It tells us about the water type, where it plots. It's calcium, magnesium, bicarbonate waters. That's not a surprise. Most of the waters in these Paleozoic rocks, Paleozoic aquifers are that. But there was two kind of interesting trends. And so the first ellipse, this one here, number 1, is a trend of Mount Simon wells. And so I talked about we could look at naturally elevated chloride versus anthropogenic chloride that humans caused. And so elevated chloride in the Mount Simon and very old ages. So we know that these are basically elevated chloride values from the Mount Simon that are natural. They're geogenic. They come from the rock itself. Where there's a separate trend, ellipse 2, and these are mixed waters, so that tritium age is mixed, it's green, and so the chloride or the nitrate trend is basically coming from human influences. It doesn't say exactly what that influence was, but we know that this trend of water has been impacted by humans, where this trend is a natural chloride trend. So water chemistry, that's one of the plates. There's 2 plates in your packet. The first plate is water chemistry. Not going to spend a whole lot of time on it. You can open your plates. It's basically categorized by the tritium age. That tells us about the residence time. But then we pull in chloride, nitrate, and then also arsenic and manganese. And if you read the report, arsenic is a natural substance for the most part in Minnesota. It comes from the rock or the clay itself. Or manganese can be a geogenic contaminant as well. There can be some health risk with that, and so that's all detailed in the report itself. Pollution sensitivity, that's really what we're charged with our program. What did we find for Houston County? And so the first map we do is a near surface pollution sensitivity. And so for a lot of counties outside of the Southeast, this is developed using soil profiles, but in southeastern Minnesota and Houston County, there's really not a whole lot of soil there to approximate this. And more importantly, there's karst within 50 feet of the land surface. And so in our program, that's a special condition. And so this red area that you see across that whole Prairie du Chien Plateau is what the, pardon me, area prone to karst feature development. And that means that water can move very rapidly through that system. And so what I'll call your attention to is the bedrock aquifer, because that's where most of the water that's coming into residential houses and to cities, to irrigators, et cetera, is coming from. And so we use basically a time scale, and we convert that to adjective terms. Adjective meaning very high, high, moderate, low, or very low. And that's all based on the age. Is it like hours to days, days to weeks, weeks to months, months to years, years to decades, decades to centuries. And so we use the residence time as inferred through tritium and carbon-14, but we also couple that with the human cause, the anthropogenic loading of chloride or nitrate. And we pull those data into these different aquifer systems and then map the pollution sensitivity using that data. So one quick hydrogeologic cross-section, like a stylized one, that's important that we'll talk about in particular as we get deeper, like into the Jordan and deeper, is that edges are really complex. So, if we're in Caledonia right now, we're pretty much up on this Prairie du Chien Plateau. It's either the Shakopee or the Oneota or the first bedrock units. But as you moved east, into some of these valleys, Crooked Creek or Winnebago Creek or, any of the others, you're getting to the edge of where those bluffs are formed. And what you have is rock that's kind of fractured, like Julia talked about earlier. And what you have is kind of a mixing on those edges. Edges are complex. You have younger impacted water that's kind of taking a shortcut on those edges and mixing with older water that's been recharged a long time ago, or even recharged outside of Houston County, you know, in Fillmore County or Mower, and is moving very slowly as it's going to move and discharge in the Mississippi River. So just wanted to kind of give you that conceptual model before we look at the results. Let's look at the results. Pollution sensitivity of the Cummingsville through St. Peter. So that's really just kind of your Spring Grove neighborhood. As Julia talked about earlier, the Cummingsville, Platteville, and Glenwood are karst systems. The St. Peter's technically a sandstone, but throughout southeastern Minnesota, there's been a large number of sinkholes that have actually formed in it. And so it's not a karst sinkhole, it's a pseudo-karst sinkhole, just a fancy term meaning that you can move water through a fracture. And so we lump those together here using all that logic, and that's detailed in the report. But basically the take-home message is that the pollution sensitivity rating of that lumped aquifer system is very high. And we know that primarily just because it's fractured karst, it's close to the land surface, less than 50 feet to the land surface, and we have elevated anthropogenic chloride and nitrate where available. Let's move into the Prairie du Chien aquifer. Now, in the report, you'll see it's broken in part. Julia talked about it broken in part as either the Shakopee or the Oneota. It's lumped together here for simplicity. But basically, it's that same story. This is that same area in the footprint of the regions prone to karst feature development. And so it's dolostone and limestone. It's soluble. You have sinkhole development. You have fractures that are getting enlarged. You have a fair amount of sinkholes in the county. I showed you the histograms of those earlier. And we have residence time indicators of at minimum all mixed waters, but we have elevated chloride and elevated nitrate in all those waters too. So we know that humans are elevating chloride, humans are elevating nitrate, water can move quickly through the rock itself, the aquifer itself. And so this is a very high pollution sensitivity rating as well. Most people that put wells in nowadays, there's definitely Prairie du Chien wells left in the county. Wells are very expensive to drill, right? No one's going to tell you, no one from an agency is going to tell you you need to get rid of a Prairie du Chien well. But if someone's putting a new well in, they typically jump right past Prairie du Chien because we know this. There's elevated nitrate, there's elevated chloride, the water's younger, and if you're putting that investment in a well, you're going to go deeper, to limit those impacts. And so let's go deeper. The next one's the pollution sensitivity of the Jordan aquifer. And the Jordan aquifer is kind of a mixed bag. We do have some very high, and this is that little schematic that I showed you a little bit, like 4 slides ago of edges, right? And so on edges, you have water trickling down from the shallowest aquifers and moving rapidly and mixing low. And so that's what that thin veneer is. The red, you can almost barely see it. It's just a thin veneer around the orange where the sensitivity is higher. And it's higher because the Prairie du Chien above it is karstic. It's fractured, there's dissolution, it's been impacted already. And so what do we find in the Jordan? The Jordan is a little bit of a mixed bag. It really depends on where you are in the county. So what we found is that when we have the full thickness of the Oneota and at least 30 feet of the Shakopee above it, there is some protection based on tritium values and nitrate and chloride values. But where the Shakopee is thinner or the Oneota is the first unit, there's elevated sensitivity. And so that's how this was delineated. It was basically delineated using water residence time, chemistry, but also iteratively in that GIS environment, that geographic information system environment, by changing those thicknesses until there was kind of a best fit with the water chemistry that's available to us. Yet there are outliers, right? Like right here, this black number is an estimate of 2,500 years. There's a 2,000 years here. That's a dead tritium, so that kind of makes sense. Spring Grove would have that full thickness of the Cummingsville and Platteville, Glenwood, St. Peter. So it's just a lot thicker of a time period for water to move down. And so it's a little more protected in those thicker areas versus kind of the thinner areas. But get ready for the big jump. This is where you'll really see the impact of the St. Lawrence aquitard. And so right now we're looking at very highs, and moderates, right? Yellows and oranges primarily. Underneath the Jordan is the St. Lawrence aquitard. Let's move to the next deepest aquifer, the Lone Rock. When we jump to the Lone Rock, you see that nearly the majority of the county is very low. And very low means a century or more of groundwater residence time. We collected a number of carbon-14 dates at those samples. And so you see groundwater residence times of roughly 4,000 years in these green areas to 16,000 years over in Spring Grove. And so that means that St. Lawrence aquitard is being very protective in a vertical sense. You know, the Jordan has some impacts above it. We see that all throughout southeastern Minnesota with basically nitrate values climbing slowly over time. I think it's roughly like 2% per year. But jumping across St. Lawrence, we have dead tritium, so waters that are definitely older than the 1950s. And in many cases, when we sample using carbon-14, they're millennia. What about the edges though, right? We talked about those edges, the valley edges being complex and lots of leakage. And sure, we see that all over the place here, right? Nearly all these elevated values are springs. That's the circle with the little kind of flagella on it, you know, like a tadpole. And those have chloride that's elevated and nitrate that's elevated. And so we know that there's basically leakage that's occurring, leakage of waters that are younger and impacted by human influences, moving laterally to that edge and then moving across the St. Lawrence and into the Lone Rock Aquifer. So now let's go deeper, right? Beneath the Lone Rock Aquifer, this was the Franconia. Now let's move deeper to the Wanawak, which was previously known as the Ironton Galesville. Kind of the same story, right? Mostly very low, century or more. We do have not as many. We don't have a carbon-14 in this neighborhood. In fact, we have an anomalously low one. Most of the values are like in the 4,000 to 5,000 range. But you'll see that it's primarily dead tritium. There's a couple outliers though. You see that there's a green tritium value here. This means a mixed tritium, and it's in an area where we should have very low. Over here, this value is just kind of unusual and quite honestly, not quite sure what's happening. What's happening here? Well, you'll see there's a little symbol connected to it. It's a little plus sign, and it means we don't know. What does that usually mean though in our program? It usually means that, you know, wells aren't perfect, right? You know, wells are put in, wells have lifespans just like everything else. And often where well joints are connected, you could have like a galvanic cell reaction where basically, you know, you get a little hole that forms in it and water can leak. And so usually when we have one of these kind of anomalous values, it means in most cases that there's something compromised with the well. Maybe the well wasn't grouted properly. Maybe there's a fracture or crack in the well, but it's allowing water to basically kind of circumvent that St. Lawrence aquitard and move rapidly into a deeper aquifer.
Is that what occurring as well with the Caledonia wells? That's recent.
Yeah, that one's exactly. That's what I'm talking about here. This one's in like a gray space between. So tritium's like roughly pre-70 years or post-70 years. The accuracy of carbon-14 data, you can only do like roughly 100 to thousands to millennia, and so the carbon-14 value here just can't be estimated well. It could be like in that 30-year difference, right? We know the water's older than 70, but it's less than 100. So this one's not as unusual, but this value here, in almost all circumstances, when we come up with these kind of unusual values, have something to do with a compromised well, whether it be grouting or the well itself. We've got one more deep aquifer to go to, the Mount Simon aquifer. There aren't many wells in the Mount Simon, certainly in the bluffs, right? Like if you're up in this Prairie du Chien Plateau or the Upper Carbonate Plateau, who wants to put in 1,000 deep well? No one's got just extra money laying around to put in 1,000-foot deep well, right? So you really only see the Mount Simon either associated with a municipality that is serving water to customers or in a valley, right? So you see them along the river valley where all that rock's been eroded away and you don't have to drill as deep, or along the Mississippi River Valley. But the story is basically these are really old waters, right? We've got a 30,000 value, two 30,000 values, $18,000 year value and a 12,000 year values. You'll also see that there's elevated chlorides, right? You don't see any nitrates. That is completely consistent with the Mount Simon, very old waters, very protected under multiple aquatards. But you do see this little asterisk next to these chloride values. And that's what I was talking about earlier in the slides when there was a kind of complex graph of chloride versus chloride to bromide values. And so in the Mount Simon aquifer throughout southeastern Minnesota, not just Houston County, there's naturally elevated chloride. And that's from those seas that we're forming. You know, like if you go, you fly to Florida right now and you're playing in the sands at the beach, you know, you're gonna get some salt water in your mouth if you're, body surfing or something. And so there was salt in those waters, and some of that salt water kind of hung around, and that's why there's elevated values there. So that's the pollution sensitivity to these aquifer groups. It's really it's consistent with kind of what we know elsewhere in southeastern Minnesota. And so let's take a quick look at multiple aquifer wells. Multiple aquifer wells, we sampled a few of them. We tried to limit that because we can't glean as much information about it, but they are helpful just to know what might be happening in terms of cross aquitard water movement. And so we're no longer able to put in multiple aquifer wells. Department of Health has prevented these since 2008. And why is that? Well, it basically is because water in those shallow aquifers can bypass an aquitard and move into a aquifer that's deeper. And so we kind of see that in these multiple aquifer wells, and that's why they're no longer allowed. Hydrogeologic cross sections. I'm not going to spend a whole lot of time on this. We'll have a short break shortly here, but it's kind of similar to what Julia showed earlier. And so that is the second plate that is in your packet. You open them up, and a cross section is just like kind of like a layer of cake, right? Most of the maps that we're looking at so far, you're looking down on the cake. The cross section is kind of like that yummy goodness once you cut the cake. And so these are the different aquifers and aquitards. They're symbolized, there's a legend that'll tell you how they're symbolized. But what we've added is color coding that matches those tritium ages. And then we've pulled in chloride and nitrate and the other values that we can help interpolate. We also have equipotential lines. What direction is groundwater flowing? Kind of like along that cross section. And I guess one of the key take homes is if you look at the cross sections, there's 6 of them. Yeah, 6 of them. If you're in the northern part of the county, these valleys are super incised, right? Like they were eroded away. But as you move south, like towards Caledonia, there's just like a lot more rock. And so that means there are aquitards underneath this Prairie du Chien Plateau and upper carbonate plateau that aren't really available up here. And so in the northern portion of the counties in these valleys, it means that young water can get a little bit deeper just because those aquitards are gone, right? Water comes down the valley. Some cases it sinks in these streams. And so there's a little bit of a change in geochemistry just depending on the thickness of these rock units. That's a takeaway. There's not a whole lot more to say along this. And so let's just zoom in on one. So just randomly chose cross-section BP prime. It basically kind of goes down the Root River Valley. Root River kind of crosses it a couple times through Houston and Hoka. And so kind of the same idea though, you're not down towards Caledonia yet. And so there's a lot of valleys in that neighborhood. So you can think that, when there's rain or snow melt, water's moving through the rock itself, but in these valleys and sinking in these valleys. And so you get, younger waters in deeper aquifers in this northern section of the county than you do in the Caledonia or south. And it's just solely because those aquitards have just been eroded away over time, for thousands of years. So it's the natural system that's causing that. Yeah, and that's basically what I was saying earlier. You know, we plot the tritium ages based on the residence time age based on tritium. We pull in the carbon-14 values, which are the black bold values, and then we pull in the chloride and nitrate as we talked about in the map views. Groundwater level and groundwater use. We're almost done here, folks, and then we can have a break. Groundwater level. So there aren't a whole lot of groundwater leveling wells in Houston County. There's limited land for them, and they're also very deep. But we do have a good example here for you. And so this wellness is over near Brownsville, up on the bluff. So these would have been spendy wells when they were put in. Period of record goes back to the early 2000s. And so what you have is a lumped Prairie du Chien well. So this wouldn't be allowed according to modern Minnesota well code. But what you're looking at is water levels in the Prairie du Chien aquifer, Jordan aquifer combined. So when they drilled the well, the open hole section crosses the Prairie du Chien and the Jordan. But the take home here is that you can see that after precipitation events, you can see fairly large increases in water levels. And so that really kind of supports that karstic aquifer, right? If you have fractures and void spaces, water can move quickly into that system. And that's why you get that big bounce, that big rise in water levels. You can also have periods of less rain and precipitation, and you have rapid falls too, right? That rock is going to drain more quickly. So faster responses. Now we get deep. We are below the St. Lawrence again. And so there's kind of an interesting story here. And so we just went through the Prairie du Chien Jordan. You get basically individual events. We get down into the Mount Simon, and it's interesting. The water level is actually higher than the Wanawak, and that's because it's that confined aquifer. It's below that Eau Claire unit, which was that other confining unit. So there's, you had the St. Lawrence, and then you had another deep one called the Eau Claire. And so the water pressure in the Mount Simon is actually higher than that in the Wanawak. And so that tells us that there's an upward gradient, upwelling. And so the Mount Simon is confined across Houston County, except at the Root River and right at the Mississippi River, where basically the Mount Simon is discharging and providing base flow to those streams. You also see that just changes in the water level of both the Mount Simon and the Wanawak is really subdued, right? That same amount of precipitation that was falling at the landscape, there's very minor changes in groundwater elevation. Now, notice there is a little squiggly line here. And so there's a big difference between these water elevation levels. So these are down near, Mississippi River Valley levels. These are higher up in the Prairie du Chien Plateau. Okay. Groundwater appropriation. And so if you're a big water user, big meaning more than 10,000 gallons a day or 1 million gallons a year, you need to have a permit for that water. You pay a small fee for that water. And so primarily the biggest users are municipalities. So, you've got people that are connected to a municipality. The municipality is charging them for that water. And so that's the case here in Houston County as well. Most water use, you'll see the blue circles are municipal public water supply. And so you see a lot of use centered around La Crescent, Hoka, Houston, Caledonia, and Spring Grove. Now there's some other uses, of course, as there are across the statewide. Livestock watering, so the yellows, that's another big one. Pollution containment. So there's a Superfund site in Spring Grove from some contamination. It was like metal plating or something. I forget exactly what it was. And so basically they are continually pumping that aquifer to keep that water from moving down into deeper aquifers. So that's a big circle. So just like the symbology on the chloride and nitrate, the bigger the symbol, the more of it there is, these graduated symbols. So the biggest circles in this case would mean greater than 50 million gallons a year. And then we can, by having that permit, it allows us to know what resources are being used. And so this is pretty much that exact same data, but we're looking at it via aquifers instead of uses. And so you can see that there's some large uses with this Wanawak Mount Simon symbology. This X is Lone Rock Wanawak. And so it allows us to see which aquifers are being pumped the most. And that helps us with resource protection, resource interpretation. And so lastly, here's a plot of all annual permitted groundwater use in Houston County. And so again, these are just the big users. These aren't the residences, the farms that are using smaller volumes. But the big users, you can see that there's kind of like a peak increase in water use in the early 1990s, but then not a whole lot of use basically through the 2000s. Use actually fell, around 2008 to 2014 or so, and then slowly has come back up. And so what causes those changes? And it really has a lot to do with precipitation use. So, if you're in one of the big cities where you have municipal water, are you watering your lawn? Are you washing your car? But it also has to do with the economy, right? If it's livestock, what are market prices? Do you want to spend a lot of money on water, or is the market down? You're not going to have as many cattle head. And so so this allows us to track water over time. So yeah, let's wrap it up. The conclusions. Geology is important. Julia did a great job explaining that. So the rock itself really governs whether it's going to be an aquifer, an aquitard, and whether it's an aquifer or an aquitard, and in particular, how close it is to the land surface really influences whether you want to have a well in it or not, or whether you want to put a new well in it or not. Houston County is actually the wettest county. That's in the report. I didn't go over that, but it's the wettest county in the state. So we've got a lot of water here. But that also means that a lot of water plus karst means that you can really move a lot of things from the land surface into aquifers. So it increases the pollution sensitivity. We definitely saw influences of human influences and chloride and nitrate throughout the county. And in particular in bedrock aquifers above the St. Lawrence, pardon me, but also in the water table aquifers. So in the river valleys, Root River Valley and the Mississippi River Valley a little bit. Springs, there are people that use springs in the county, not a lot. Most people have wells, but some people do drink from springs. Springs are really kind of a mixed bag. They typically have mixed tritium values, so more modern water that's less than 70 years old, and they nearly always had levels of chloride and nitrate that were elevated. Kind of the big take home message: the St. Lawrence aquitard is a very competent aquitard in Houston County, unless you're right on that valley edge, right? And then there you're going to have some leakage around it. And so groundwater that is below the St. Lawrence aquitard has long residence time, greater than 70 years, but also based on the carbon-14, anywhere between 4,000 and 30,000, depending on which aquifer you're in. And lastly, properly installed wells completed below the St. Lawrence aquitard can provide groundwater unimpacted by human activities. And so that's definitely a key take home, I think, for this county, that, I all throughout southeastern Minnesota, you've been reading about it for a couple of years now, the EPA petition, et cetera. The Prairie du Chien and the Jordan have problems. I think that's been known about for a while. Levels are climbing. The good news is that you've got a really competent aquitard, and that water below that aquitard is really unimpacted. So if you put in a well, that's built to code, grouted properly, et cetera, there's a lot of good water down there.
How deep would that well be in Caledonia?
Okay, so I'm going to repeat questions so people online can hear. And so the first question was, how deep would a well like that be in the Caledonia area? Julia would probably have a better idea. So if we're below the St. Lawrence, probably like 600 feet, something like that. Yeah, ballparky. And do the math. Yeah, roughly 500 feet in the Caledonia area. Second question.
Could you get on? I understand these deeper wells people are putting in have a lot higher issue with iron and some other things. So they're safer, but we have to do treating.
Yeah. So that's a great question. I barely touched on it, but like as I mentioned earlier, we look at manganese and arsenic. And so the one slide I said, when water hits the surface, it starts dissolving rocks and minerals, right? And so the longer water is underground, for example, under that St. Lawrence aquitard, those waters are a lot older waters, right? But that means that along their flow paths, they have dissolved parts of the rock. And as part of that, you get higher iron, you get higher manganese, you can get, if in some of the deeper aquifers, you get something like called radium or radon. And so there are issues, and that's why I highlighted human caused contamination, because this is like pollution sensitivity to things on the landscape. There is a trade-off as you are getting deeper. So yeah, depending on what the element of interest might be, whether it's iron or arsenic or manganese, it typically does require treatment. Treatment could be anything from like oxidation to reverse osmosis to a number of different things. And so that could be a trade-off too, right? Like my understanding is there are some resources as part of this EPA petition. In some cases, a well owner might not have money to put in a deeper well, and it might be cheaper to do like RO, knowing that you're gonna, your water's younger, but yeah, our pollution sensitivity is more geared towards human influences and not towards geogenic. Geogenic meaning natural elements that could be elevated. Some of that data is available. Not trying to push you anywhere else. You could contact us directly and we could, send you links to it. But like the Department of Health has a better guidance because that's what they are. They're health, and often some of these are health related questions. So, yep. Next question.
Go ahead.
This is related to your last statement. What's it taste like? I mean, it might be water, but is it potable and suitable for human consumption as it comes out of the ground?
Yeah, so the question was, what does it taste like? Is the water potable or suitable for human consumption? And so, I mean, that's a very fair question. That's a great question. The favorite water I drink is at my father-in-law's cabin in Wisconsin, which is a shallow well in sand, just pure sand. And why is that? It's because it's very young water. So I'm basically drinking precipitation, right? However, he does have a septic system, so it always makes me wonder. And so, but as you get deeper, for instance, each of these units, as you're getting deeper, as you're changing that chemistry along that flow path, you are picking up things. And so iron, obviously, iron and manganese, that'll impart flavors, right? Like some pretty strong flavors, whether it be metallic or, bloody. And it also like impact, washing your clothes or like, whether you're staining in your sinks and toilets. Really old waters can have sulfate, a little bit of a rotten eggy smell to them. And so all this is a trade-off, right? And so it really depends on whether you even have funds available, right? Because wells are expensive here. And then, like, I don't even want to use the term risk, because it's not risk per se, but it's just what is important to you. Would you rather have younger water that may have some impacts from human influences versus a deeper well, if you even had the money available, where you might have some off-putting, taste. Some of those things could be dealt with through RO and other things as well. And so there are engineered solutions, but those come with cost as well, right?
Well, I think I could speak for everybody wants clean, safe water.
Yep.
And government is brought about to make sure the playing field is level for everyone.
Okay.
So I think it should be regulated some.
So we had a statement that, that everyone wants clean water and that, his opinion is that it should be regulated somehow. And, yeah, you know, there's other people listening to this and a lot of people that agree with you and, yeah, well, that's noted. Thank you. Next question.
I have two questions that are somewhat related. So the first one is regarding the capacity or the reserve of these different aquifers. Like out west in, say, Nebraska, Kansas, there's a lot of concern about the ability of that huge aquifer to manage or to be able to continue to supply all the usages going on. So is there data available for these aquifers and what that capacity, or I'm not sure if there's a different term for that, but I'm curious on that. And then I have a second question related to that.
Okay, so the first question for people online was, is there capacity? Basically, is there yield in these aquifers for the different uses, competing uses, you know, like relative to what we're seeing in the West and Southwest? And so our group doesn't explicitly answer those questions. However, we do have a technical analysis group at the DNR that does look into that sort of thing. And so in particular, when there is a well that's proposed, whether it be a municipal well that's pumping a lot of water or a irrigator, data center or whatever, you know, that triggers that group that looks at it, and they use all these, you know, special governing equations and understanding of the aquifer properties to basically determine if you're pumping at 1,000 gallons a minute, what would the drawdown be, and like how is it going to impact water levels in that aquifer? And so that work is done, but it wasn't done explicitly as part of this project. But that question could be proposed to, you know, our technical analysis group. And, you know, so if you reach out to me following this meeting, I could direct that question to the appropriate person.
And so kind of related to that, and you mentioned data center, which is a big concern these days, and the amount of water usage into those data centers for the cooling purposes. So when we think about data centers on the landscape, and potentially there may be one at Mabel, they're using a lot of water. Is the intent then that when they put wells in, that they may be looking at those upper level aquifers that are contaminated in a sense with the nitrates and the chlorides, instead of having them pushed down to, say, the you know, the lower ones that are protected by the state boards?
So just for those online, this is a question using data centers as an example. And the question basically is, do the people that review these groundwater appropriation requests evaluate whether shallower aquifers or deeper aquifers may be more appropriate? And the answer is yes. And in fact, the Mount Simon actually has a moratorium on it. So you couldn't put a data center, a well into that for data center use. It's basically saved as an old water continuous resource solely for human consumption, unless you're in some very unique, you know, where the Mount Simon is the first bedrock unit, then that's exempt at that edge. So the answer is yes, but like it would depend on where in the state is proposed, what's available above it, what the yield is, how much water they want to use, et cetera. But yeah, there's a whole team of people. There's like environmental regulators that kind of start the process, but then all that stuff goes to our technical analysis group, which is a group of like, I don't know, 20 people or something like that statewide that are all really versatile in groundwater modeling, groundwater, you know, computation, et cetera. And they determine what those proposed impacts would be, whether or not there's enough specific yield in the aquifer itself to not have impacts from the request. Thank you.
Just a note from Jay online, who's on our team. He said that we monitored our observation wells to track pumping impacts on the aquifers. So there's that. And then I have a question via Teams. There appear to be fault lines indicating the number of the cross sections. Did they see any chemistry differences in the samples pulled for wells near the faults?
Yeah. So did everyone hear that? Okay, so it sounded like someone online is wondering, acknowledged that there was a bunch of faults. Julia showed the faults where there was offset in the geologic units. And the question from online was, is there water chemistry differences near any of those faults? And my recollection was there's one cross-section line where there was a water chemistry difference across it, but it's not clear. We would need additional information to know whether or not that was like leakage either through or across the fault.
May be aware there's a proposed project, the Maribel transmission lines across just the county. And as part of that transmission line, what they're going to, how they're going to support these structures is they're going to build, or they're going to be cement, they're going to drill cement piers into the bed. They're going to be up to 8 feet in diameter and up to 50 feet deep. And there's going to be 4 of them per tower, so you will have. So my question is, do you have, either of you have any concerns about hydrology in this county, especially since some of these towers are going to be right down at the level of the creek?
So for those of you online, there's a question from the members here related to a proposed transmission line that sounds like it'll be running up the Winnebago Valley, which is kind of that prominent valley in the southeast portion of the county. Yeah. And so in particular, the person asked whether Julia or I have concerns about the footings that may be put in with the towers. And I personally would need to know more specific units, like more specific information, where exactly they're putting them relative to the geologic units to answer that in a meaningful way. I will say that transmission energy projects, there's like a separate entity that forwards those to the DNR, and that goes through a regulatory review. And as part of that process, regulatory review typically reaches out to Groundwater Technical and Groundwater Atlas for input. So without knowing more details, I'm hesitant to answer it right now.
Engineer, but as John said, now that we have this updated mapping, hopefully this company will use that, right? And the Minnesota Geological Survey is non-regulatory. We don't generally get pulled into any of these types of projects. We just put out the unbiased scientific information and hope that it's best used. Right, engineers would pay attention to, I'm assuming they would pay attention to water level, where they're putting these in. They pay attention to the rock type, whether it's sandstone, limestone, and they have to engineer it differently. But not an engineer, so I have to start, but those are definitely things that they should be aware of. And also Karst, you know, that potential hazards in that direction.
The DNR ever issuing an opinion against putting that type of structure in the Karst area?
I'm not part of the right environmental group, so but you could certainly message me and I could ask that question to see if those have ever been turned down.
It's a question, I think, right before the meeting started. We'll get back to you. Thank you.
On the GIS layers that are available online, are there KMZ files that allow import into, say, Google Earth?
I don't believe so. I believe they're feature classes. So typically, you know, Esri products, ArcPro, ArcMap. If there was something, most of the time there's a tool within Esri products where we can convert to KMZs. Depending on, if you reached out, I could see if I could convert it for you. You know, feel free. You know, my contact information is available through all this, or you could just go to the webpage and contact me through that. Oh, I'm sorry, I didn't repeat that question. Someone in the audience was wondering if the GIS files are served as a KMZ file, which is a file type that it plays well with Google Earth. And so you heard my response. Just
We, same with our stuff too. If you're needing any of the geologic information and you're not, you know, the Houston County stuff was put together several years ago, so I don't think, I can't. Downloading it, you may have issues, but just shoot us an email. We have 3 GIS stuff technicians that, are on the ball with all that stuff. We want people to use it. We recognize that there are technical issues sometimes. So definitely reach out.
Any other questions for now? So we could take a short break and then we have just a follow-up kind of hands-on, like a hypothetical situation on how to use the atlas. So feel free to stick around if that would be useful to you. Appreciate you coming or attending online. Let's do a hypothetical spill. And so some tanker truck spills an unknown liquid just south of us here on Highway 44, right at that sharp curve. Figured that would be a potential place for us. And so let's say you work here at the county, you know, you might have a police officer or a firefighter or someone contact you, MPCA duty officer, and they're going to want to know, hey, where will this go possibly if it goes anywhere? And so how can you use the atlas, in particular the part B, but you can see how linked part A's and part B's are together to maybe answer some of these quick decisions. And so, the first question you might want to ask her is like, what surface water features might be nearby? You know, if that product moves, is it going to hit, like run down a ravine and impact a surface water body, trout stream, whatever that might be. And so you can, so the little circle, the red oval on the screen is basically kind of highlighting where that sharp curve is in 44 just south of us. And that's where our hypothetical spill is. So surface water features, what's nearby? And so at the scale of this map, it's hard to tell, but I zoomed in a GIS environment. And basically the landscape, it looks like if water were to move over that surface, if it didn't sink into that karst aquifer underneath, which direction would it flow? And based on the LiDAR surface, which is basically the topographic surface, it looks like liquid would probably flow towards Cricket Creek. And so you would be able to basically focus, potential monitoring or letting people know that have wells between where the spill happened and where it may flow, to potentially, maybe limit drinking from their well until you have a better handle on what's happening. Being we know about the karst story here, is that area prone to karst? Well, in this county, a lot of the county's prone to karst. So here we are in that same circle again, and sure enough, yeah, the area is prone to karst, and there are also a number of map sinkholes in the vicinity. Although there aren't any explicitly on that curve. If they were right on that curve, then that you would have a heightened level of sensitivity to that, because water could potentially move across the surface and drop immediately into underlying aquifers or aquatards. And so what about the groundwater table, the bedrock water table in that area? And so if you pull in, open your report and look at figure 7, the first water table bedrock aquifer would be that Shakopee aquifer, so part of that Prairie du Chien system. And so on that curve, you can see that you're sort of on a groundwater divide. And that means that water, like if you're heading south on 44 from Caledonia, at some point, if water fell on the surface, water could go either direction. It could go either to the northwest or to the northeast, but you are a little bit on the eastern side of that divide. And so I'll use, I don't have my, bear with me a second here. I'll turn my pointer back on. There we go. And so what I mean is that a groundwater divide is this area here where water, if it fell on the surface, could move this direction or this direction. But on this curve, you're a little bit on the east side of that divide. So groundwater that's recharging, getting into the aquifer in this spill area site is likely to move, either kind of east or southeast. And so that's what you would take, and that would help inform where you might want monitor, so you could have water that sinks into the aquifer, moves laterally, and then could reappear at Crooked Creek. But it could also, depending on where it fell right on that, in that area, it could also go to Winnebago Creek. So this would at least let you know that you would probably want to take a peek at residential wells, in this area, but also potentially looking at Crooked Creek itself and Winnebago Creek itself. So that's that answer. And so, sometimes these aquifer systems, in particular these karst aquifer systems, are very can recharge very quickly. We saw that in the hydrographs. We've seen elevated pollution sensitivities with the chemistries, and so you may want to peek at the next deepest aquifer just to see, is that groundwater flow direction the same direction? Would that impact how I make that decision? And in this case, it's pretty much the same direction. It's primarily east or southeast. What about the near surface pollution sensitivity? What about that shallow soil or bedrock horizon at that hypothetical spill site? And here we know, just based on what we learned earlier, is that, pardon me, this area is all that area prone to karst feature development, and so that means that it's a special condition. It's a very high sensitivity, and so that would heighten, your how you may deal with this phone call. So what's the pollution sensitivity of bedrock aquifers in the area? And so we are near Caledonia, so we're not near Spring Grove. And so that means the first bedrock units, based on what Julia showed us earlier, it was either that light blue or the darker blue, Prairie du Chien, right? And so pollution sensitivity of the first bedrock units would be that Prairie du Chien aquifer. And so the pollution sensitivity in this neighborhood is very high, right? We have sinkholes in the neighborhood. We have tritium values that are mixed values. We have elevated chloride. We have elevated nitrate. We know that it's a karst aquifer. It could have vertical fractures, dissolution conduits. And so whatever that hypothetical liquid is could potentially move quickly into that aquifer. There are many sinkholes in that neighborhood. Now let's use that same logic. What about a deeper aquifer in that same neighborhood? And so right on that curve, this hypothetical spill curve, you'll see that it transitions to moderate. And so what that means is that oniota, that lower brown colored geologic unit that Julia had described as an aqua tard earlier, that is offering some protection to the underlying Jordan aquifer. So your immediate response, you could probably be maybe more focused on Prairie du Chien wells to the east and linkages to springs, from the Prairie du Chien. If you had deeper wells deeper than the Jordan or deeper, well, that would buy you some time, so to speak. You wouldn't have to think like, boy, we should get a hold of these people and let them know that, maybe they should avoid drinking their water until perhaps a duty officer or MPCA or someone gets involved. So this is just linking us back to the cross sections, and it would be finding which cross section is closest to the area of the hypothetical spill. And so it would really be using kind of the inset within the map, and so you would find Caledonia on the map. You would find the closest cross section line, and then you could see if that would help you either make some decisions or maybe help you get in contact with someone that could help answer questions you may have. So if something happened like that, you may want to reach out to our group. Hey, we did have a spill on that corner, can you help us out or something like that? And we could offer our opinions on how the atlas could help you make some decisions until the duty officer or someone like that got involved. Now, with that said, let's say you had a spill over in Spring Grove. Well, there you have a cross section a little bit to the east, cross section E prime, or a little cross section to the south. Oh, I said east, I mean north. I used the letter E as east. So you'd have cross section E prime to the north or cross section F prime to the south. And so you might actually want to take a look at both of them just to see if, one of them has a little bit more information than the other that could help you make some educated decisions on how you want to respond to this hypothetical situation. So in this case, the curve is roughly, you know, right on State Highway 44, right on that curve. And so here, you know, you have very little unconsolidated sediment, you know, just like a lot of the rest of the county. It's less than 50 feet thick. You do have a little bit of shakopee, and so that's the little pink lines that are within this OPS. That means Ordovician shakopee unit, the Prairie Shane shakopee unit. Underneath that is the Oneota. And so the Oneota, although it is part of the karstic unit, is a tighter unit. And so it may buy you a little bit of time as you're making some of these decisions. What about groundwater users in the area? So here we are on that oval, you know, on that curve. And so what are the big groundwater users in the area? So it looks like you've got a little bit of golf course irrigation to the north, but we've already learned that groundwater is probably going to flow east or southeast, just like surface water if it actually made it across the surface. But what I didn't mention earlier is that high volume users can basically create a change in how groundwater moves in the land surface, and really high users can create something called a cone of depression, which means that it can change which directions water is going to flow. And so it's worth maybe peeking, you know, like, did we have a spill near a high volume user, especially if it's a municipal, you know, water supply place, or some other sort of user. So that would be worth checking into, whether or not they're permuted water users, because those are typically water users that are extracting water at higher rates, which changes that groundwater flow direction, that gradient. But these are just permitted water use. You know, maybe volumetrically, the amount of water used is the most, but most residents in the county are outside of those areas, right? And so it would be remiss to acknowledge, to not acknowledge that, like, all these other black X's are like domestic wells or farm wells or something. And so if you had a spill on that corner, you know, in this case, well, you probably wouldn't be concerned about golf course irrigation, you know, but you would probably be interested in knowing that you might have a number of domestic well owners that live to the east, somewhere between Crooked Creek and Winnebago Creek. Now, with that said, this map isn't in the atlas, but as we continue on this little workshop, I'm going to show you where you would find that data. And so that data is available online, and it would tell you what the well depth is, what aquifer it's in, and that could help you make some educated decisions. You know, if they're below the St. Lawrence Aquitard, do you think it's a big problem, something that needs to be acted upon immediately? Probably not, from what we've learned, right? That water's much older and much different than the water above it. And so, you know, they might have a bad well casing, but, you know, looking at the big picture, which is what these atlases do, it could give you an informed decision on where you might want to focus as you're making these educated decisions towards like a incident, like a hypothetical spill. So here we go. A good segue. I didn't realize it was built that well. Thank you, Susan. And so where to find this information about wells in Minnesota? And so the Minnesota Well Index. Earlier, both Julie and I were saying CWI, County Well Index. It was kind of rebranded to the Minnesota Well Index. But if you do a quick Google search, Minnesota Well Index, that'll get you to the Department of Health, and it'll get you into an online tool where you can zoom in and zoom out. And if you zoom into an appropriate level, it is going to let you see wells in that neighborhood. And so you would be able to search by a well number. And so this is like for some of you here that are curious about the well at your house. If your well, you know, typically like a metal pipe sticking out of the ground with an aluminum cap on it, a lot of wells have a little blue plate on it with some numbers on it. If you put the numbers on that little blue plate plate in this tool, you could go to the search by tool, you could put that well number in, it would pull up that information immediately. Now, sometimes those well numbers aren't available for old wells or for wells that, like, it just, you were riding your mower too close to it and you scrape the mower, the plate off and it's no longer there. Well, the good news is you can zoom in on a web map. So you could zoom in and click on that dot, like at your farm or at your residence. It would pull up that well and it would show you the data that we're about to look at. So to link this back to some of that well groundwater elevation data that I showed you earlier, we're going to look it up using one of those wells, but you could do that. Oh, one other thing. If your well is super old, your well might not be in the database. And, you can't really do much other than that, other than maybe look into your old, file to see if the previous owner might have provided that with you when you bought the house or your grandpa gave it to you or something like that. Okay, so with that said, let's learn about a well in the Minnesota Well Index. And so let's zoom over to that well nest over near Brownsville that I showed the groundwater elevation hydrographs to earlier. And so the well nest is just there north of DD Prime, just south of Brownsville. And so if you zoom in that Minnesota Well Index, you're in the map view, you could either kick in this number, like if you're doing it right now online or on your computer sitting here in the audience or on your phone, you could go to the Find My and type in 231847 and it would get you to this, or you could zoom in on the map. There'll be 3 of them and you would be able to click on the one that's 231847. When you click on it, it's going to open up a web page basically of all the information that's available. So I'll point out a couple things. The well ID. So that's if you know your well number, you could key it in. And so here's the one that we're hypothetically looking up. Here's that well number, 231847. Now, if you look at your well tag, there's actually going to be 4 zeros in front of it. It's a 10 character number. Often we just kind of ignore those first 4 zeros. And so then you're going to learn information that's part of the database. So what's the elevation at the land surface of that well? You'll get township, subsection, the driller who put it in, well name. So well name would often be like the parcel owner's name. Now, of course, parcels change owners over time, right? And so it might be under the name of the person you bought your property from, or your grandpa's name or something like that. But here's all the important stuff though. What's the depth that was drilled? And so the depth that it was drilled lets us know which aquifer it's in. That Julia used basically this information to determine how thick these aquifers are. And so that'll let us know which aquifer it is. And so that's populated by people at the Minnesota Geological Survey working in partnership with people at the Department of Health. So at this location, a 565-foot depth well is in the Wanawak aquifer, the Wanawak sandstone. And so that's linking the depth to the aquifer. Now, then there's additional information. In this case, it's an observational well. If you were looking up your own well at home, it's say domestic here instead of observational. Entry date's not that important. Of course, we're in Houston County. Sometimes the completed depth is different than the drilled depth. And so sometimes a driller will drill like through the Jordan sandstone into the St. Lawrence, know they're in the St. Lawrence, and then they'll complete the well a little bit shallower than what they drilled. And then that way they know they're completely in the sandstone unit and above that St. Lawrence, or vice versa, below it. The status, et cetera. So it's going to give all this information to you. But from that, then you're able to access actual things about it. So for instance, the well log report. So if you clicked on the well log report within this highlighted red box, it would bring up the well log report. And so here it is again, that same number, right? And here are basically the driller's description. And so at this site, there was 15 feet of unconsolidated material. So sand, gravel, loess, et cetera. And so that fits with that less than 50 feet to bedrock, right? Boom, at 15 feet, you hit the New Richmond. That's part of the Prairie du Chien unit. And then the New Richmond, is roughly 17 feet thick. From there, you got into the Oneota Dolomite and the Jordan through the St. Lawrence. And so this is the geology that helps Julie and others at the MGS create these geologic maps and these geological thicknesses. And then the rest of it's just super good ancillary data that helps our program, helps you as landowners, helps people at the county for well-specific, inquiries. So,
I'm just being nosy, looking at neighbors.
oh, okay.
And things aren't listed, like there is no aquifer listed or anything like that. Is that a red flag?
So it would depend on,
Yeah.
so that's a great question. I brought it up. Those of you online, a person here is following along with her computer and pulled up a neighbor's well and noted that not everything was populated. So things can only be populated if that data was available from the well driller. And so prior to the 1970s,
Yeah.
1974. So wells prior to 1974 don't always have all the information that's required
This is more
nowadays.
recent, but okay.
Yeah. And then sometimes just well drillers just don't populate everything. And then it can be like a little bit of a tug of war between MDH and the driller just to say, hey, get your paperwork done. But if once that information comes in over time, you will see entry date, update date in this upper right-hand corner. As information becomes available through the MDH or the MGS, they'll update these records as more information becomes available. Oh, that was perfect. You threw me a softball. Thank you.
At least it wasn't a hard ball.
John, just a quick addition on that. The actual units are not always called out in this view of the actual report, the well log report, but on that page that John priorly showed when he clicked into this well log, there's also something called a strat report.
Yeah.
So a lot of times it's very common to just see something like sand rock or shale or just a broad general description in here instead. And that strat report that's also available on the website will often get more into the specific units.
Awesome. Thanks for that, Vanessa. Julia, anything to add?
Just following up, if you can often figure out what the aquifer is based on the
Yep.
open hole interval and then kind of compare it to the other neighbors.
Yeah. And I was just about to say that if you know the depth of your well, but the aquifer code isn't filled out, often drillers will say, hey, we've got a lot of yield, a lot of water available. It's good water, it has lower nitrate or something like that. You'll see drillers will drill at that same depth, like in clusters. And so if you don't have information about your specific well, but maybe you had a driller come out and change a pump once, and you know the depth of your well, well, then you can often use a neighbor by proxy.
Jay online. Jay,
Hey, John, this is Jay.
Yeah. You're on microphone.
Yep. Just one more thing. The state does not publish municipal well information. A couple of people were asking about the Caledonia wells. I did go in and check to see if they would come up, and they are not listed. And it's a security issue.
Yeah, that's like post 9/11, the legislature got together and said, hey, you know what? We probably shouldn't let people know where well houses are. And so for municipal wells, that information is not available explicitly through this database. But often, like if you live in, Caledonia or something like that, they often have like wellhead protection plans or water quality reports where you could learn at least which aquifer the well is in. Thanks, Jay. And Vanessa. Okay, so keep going here. Yeah, just another example of how to look at your cross-section plate. So again, this was just south of Brownsville at that well nest. And so we're super close to cross section DD prime. And so there are the wells actually. You'll see this stick figure would be the well casing. The gray kind of rectangle at the bottom would be the open hole. How much it's open within the Wanawak sandstone itself. And so here we do have a carbon-14 date. Water extracted from this well and analyzed for carbon-14 came up with roughly about 5,000 years before present. At that same location, there's an even deeper Mount Simon well that you would be able to click on as well. And carbon-14 analysis for water collected from the Mount Simon was 30,000 years. So just kind of a way to kind of retest your using these plates now that you've been informed about them. Let's see here. What else do we have here? Circling back to the stratigraphic column. So figure 3 on page 8, just looking back about how we've learned what we learned from Julia on these geologic units, and then how they're either colored as blue as aquifers or brown as aquitards. And so you'll see that the Wanawak sandstone is primarily an aquifer in that neighborhood. And so just kind of linking back to that, increasing your knowledge on the report and how to kind of move back and forth to use it in each direction. Let's pull in so I showed you those groundwater hydrographs. And so it was a combined Prairie du Chien Jordan that was kind of with steep climbs and drop-offs over time. And then there were 2 other levels. One was this Wanawak well. The other was the Mount Simon well. And so if you wanted to access that information, if you're curious about it, want to learn more, you could go to the DNR's cooperative groundwater monitoring site. And so there's the link. And if you go into that, it's kind of the same deal. It's a web map tool. And so you can zoom in the state and see what wells might be in your neighborhood. Again, there's not a lot of them in Houston County, but there is this nest here near Brownsville with 3 wells. And so you could zoom into it by using this plus sign in this upper corner, or and then that would get you into the map view, and then you could click on it. That would open up a little box that would tell you information about it. So CWAC means Cambrian Wanawak. And so that's just an abbreviation that means the same thing, the Wanawak. And then it tells you what the, that unique well number is, the 231847. That might sound familiar by now. It'll tell you how long it's been monitored, what the elevation at the land surface, where they monitor from it, and then what the depth of water level is, or at least the water level elevation. But it'll show you a hydrograph over time. And so this one might look a little bit peakier, look like it has a steeper value than what I showed you earlier, but that's all dependent on what the scale is on this y-axis, right? So there's that. Hey, what direction is water moving there? So then you could circle back to figure 11, right? And that would be the potentiometric surface, what that water elevation is within the Wanawak, since that's the aquifer of interest. And so the nest is basically in this neighborhood. There's not a ton of data, so these contours are a little more squiggly than they probably are in real life. It's a function of what data is available, of the density of that data in that neighborhood. But in a general sense, it makes sense, right? Water this deep under confining layers is flowing east towards the Mississippi River. And that's consistent with what we see both below and above it. So yes, it's moving east. What about the pollution sensitivity of the Wanawak aquifer? Well, that circles back to what we were looking at earlier. You would turn to figure 28. That would get you the pollution sensitivity of the Wanawak aquifer. We are what? Above or below the St. Lawrence? This is the quiz part of the workshop. Yeah, below, right? And that's why you see green, right? Very low. And so sure enough, we've got a carbon-14 age at that exact well of 5,000 years before the present. Now, you will see, like in these valley settings, you do start to get some of that elevated tritium, but in the green settings, you have old carbon-14s or dead tritium. So just circling back on that. What about, is there water chemistry data available near the well? And so looking at it on the water chemistry plate, the 2 plates, plate 5, and so you could look at it, and for that well, you don't see chloride elevated or nitrate elevated, that, but you do see carbon-14 values. And so we may have chloride and nitrate at that well. It just means that they're not above those thresholds, right? So it would have to be greater than 1 for nitrate or greater than 5 for the chloride to be shown on there. So we are showing those values if they're above those thresholds that I mentioned earlier. You will see though that, remember that figure we were showing that like edges are complex, you know, so you get leakage from the Prairie du Chien and the Jordan down to lower aquifers. So here's a great example of that, right? Here you have springs in that neighborhood that are either recent water or mixed water and have elevated chloride and nitrate. So you see that all over the county. It's really evident in those pollution sensitivity figures. That's where it pops out the most. But all that same chemistry that's in the water, plate 5, you know, all those figures, all that chemistry is shown on plate 5 as well. Arsenic. There is a little discussion of it in the report. The take-home story is there's very little arsenic that was found in our sampling in Houston County. And that's consistent with Department of Health. If you went to Department of Health's website and looked up arsenic, you would see a map of arsenic across the state. Arsenic is primarily high in glacial aquifers. So, you know, sand and gravel aquifers underneath clay. The glaciers came from like up in Canada, the Riding Mountain area of Canada, and they plowed through all these shale deposits, and the shale basically is a component that's driving that arsenic value. So being that we're in these Paleozoic aquifers down here, we just don't see much arsenic. It doesn't mean that you won't find it, but it's typically very low. Let's see. The carbon-14 ages that we just saw in that cross-section view, Wanawak at 5,000, 30,000 in the Mount Simon. So again, highlighting the protective characteristics of the St. Lawrence, but also the Eau Claire. So underneath the Wanawak is another aquitard, the Eau Claire, and that one provides even more protection, for lack of a better term, is a competent aquitard in the vertical sense that you see large values in Mount Simon and, you know, in younger values as you move towards the land surface. Same idea, just kind of like circling back, just like putting all the pieces together, just using these different figures. Are there any large permitted well water users in that neighborhood? No. Closest one would be your municipal public water supply all the way out to Caledonia, which is way up gradient. And so, yeah, that's it. That's the workshop. Thank you, Julia, for setting the stage. You made it really easy to follow you. And hopefully this was informative to everyone here and online. Again, we do appreciate workshop feedback just because this program and these workshops are a work in progress, and we evolve each time, and we always want to make them better. So if you have suggestions, you know, complaints, whatever, put it all in there because we need to hear it to improve.
There will be no other place, correct? Thank you.
There was a question, the Houston County Atlas is now complete. And yes, it is currently complete.
Is there a refresh anticipation to the data? I mean, some of the stuff is centuries or millennium old, so I'm assuming no. Is there some plan to maintain the data set and some refresh?
Yeah, that's a great question. So there's a question from an attendee that said, will there be a refresh? Will we update this in the future? There are a few counties that have updates in the works. They're typically counties that have had a lot of wells added to them. And so as you add wells, you increase the data for the interpretations for the geologic mapping. Those are often counties that are closer to the metro area. It's just a fact of life. And because of that, there's also just a lot more other agency data available in particular Department of Health. And so for a very small number of counties, there are updates. You know, at some point, you know, it comes down to dollars available, right? And so, I don't know when one would happen, if, or even if one will happen anytime soon.
To add to that, the statewide Minnesota well index is continuously being updated at the data thing. So when new wells get put in, they'll go into MWI oftentimes. It won't come across my desk to do the interpretation of those geologic units. But if that is something we're actively trying to work out with NVH at the moment, is to try to get some of those backlog ones going. But yeah, there really wouldn't be a lot of time or effort or new wells to really, within the last 10 years, to really justify making a new map.
Sounds like an opportunity for AI.
Well, that's right.
That's right.
That's something we're looking.
All right.
Has every county in Minnesota done a well index login? Have they all done that?
Every county has wells in the county well. Okay. But for like a geologic atlas, not every county has a geologic atlas, right? So when we go into a new county, that's one of the biggest efforts we do. It doesn't get talked a lot about at these meetings, but we have well staff that basically put all that information into the database. And then the geologists will put all those interpretations, updated interpretations that match the map into the database as well. So yeah, if it's got a date within the last, 15 years, then it's CWI is relatively up to date with the map.
So to buy part A, I have to make a phone call?
Yep, just the Minnesota Geological Survey, just make a phone call and or find the PDF online are also there. And we're at your county there. I mean, we would have delivered many part A's to the county years ago, so it's possible some get county still has their one.
You distribute them to the schools? Years ago, Fillmore County schools all got one.
Yes, yeah, that we often tell the county if they're left with a lot extra, we'll say, oh, bring them to the library, bring them to the schools, and then something for the extra.
Okay.
Any other questions? All right, much appreciated. Thanks for coming.
Thank you.
Either in person or online.